program on recent trends of control systems in power electronic converters. Let me start the technical session 7 with introduction of our expert Professor Subrata Banerjee sir. It gives me immense pleasure to introduce you about our eminent expert of our today's session. Professor Subrata Banerjee sir, working as professor at National Institute of Technology, Durgapur. He received his BTech degree from NBU and ME from IIEST and PhD from IIT Kharagpur. He has vast teaching and industrial experience spanning over more than 25 years. He has published over 198 research papers, and most of his papers were awarded with Best Paper Award. He has executed several government and industry sponsored projects. He was recognized under top 2% scientists in the world in 2019 by a survey conducted by a team of scientists at Stanford University. He was nominated for Honorary Rosalind Member of London Journals Press. He is a recipient of International Travel Grant from DST, Government of India. Sir is an Associate Editor, IET, Power Electronics UK, Associate Editor, IEEE Access USA, Associate Editor, IEEE Transportation Electrification, Community e-Newsletter USA. Sir has chaired several IEEE conferences and is a member of several professional bodies. His research interests include modeling and control of switch mode converters and inverters, multi-level inverters and different modulation techniques, electromagnetic levitation, active magnetic bearing, controller design, soft computing techniques, intelligent control, power electronics, and machine drives. With this brief introduction, I would like to hand over the session to Sir for further proceedings.
Thank you for your nice introduction. I think Anil.
Yes, sir. Thank you, sir.
How are you?
I'm good, sir. I'm good, sir.
You are now at Manipur.
No, sir. No, present not at Manipur. I'm at my place, sir.
Okay. So this is maybe third day of this seminar, webinar, ATAL FDP
Yes,
program on recent trends of control systems in power electronics converter. Few months, I think 2 months back, I have given one lecture at Manipur. My today's talk also maybe the similar kind of lecture, maybe because of the topic. The topic is very much interesting. Actually, you know, the control system applications in power electronics converter. You know that control systems actually synonymous in power electronics. Without control, particularly power electronics converter in closed loop, you cannot run. Whatever may be the applications of power electronics converter, majority applications should run with in closed loop, and for closed loop applications, you must have some use of controller. Okay. Though there are a lot of changes in control systems applications wise, but my focus, my lecture will be mostly on linear control. You know, switching converters are very much nonlinear in nature, and in some cases also some converters, particularly boost and buck boost converter. You know, converter, whatever be the form, means in DC-DC applications or DC to AC applications or whatever it is, in some cases you will find that converters in mostly nonlinear in nature, because today's applications converters are used as switch mode power applications. So because of that, parameters are time varying parameters. You know, all these things are in control, and the converters, because of this nature, switch on and off at very high speed. Okay, so the converters are mostly highly nonlinear. So either you have to completely model the converters in nonlinear domain, and then you must apply all these nonlinear control, nonlinear control like sliding mode control, then feedback linearizing control, all this control. So it is coming, but believe me, that majority controls used in today's industry with power electronics converter are mostly PID control. Almost 90% controller I find still today, because of this its efficiency and easily implementable, either even in analog control you can apply. And okay, there is no need to apply, but of course you have to, for sophistication and better utilization, you must apply all the digital control using that dispace microcontroller, a PGA controller. So actually, if you want to learn, I don't know that how many speakers already covered that actual control in power electronics domain, but I will try some ideas of this type of control, and particularly mostly maybe the DC-DC converters, because DC-DC converters, you know that nowadays it is applicable to that all renewable energy applications, your home appliances, as well as EV charging applications, battery charging applications, many applications. But you don't think that this my topic is mostly is based on the control applications on that DC-DC converter, but it will be applicable. It will be applicable for any converters. Either it may be DC to AC or AC to AC or AC to DC, depending on your applications area. Okay. So with this, let us start with my lecture. I have to share the slide. Is it visible?
Yes, sir.
Sir,
Yes, the today's topic of my lecture.
sir, can you make it in this presentation mode?
Let me. This is PDF though, huh?
Hmm.
Is it visible now? Presentation mode. What should be the mode? Here it is. Is it visible now?
Yeah, sir, it's visible, sir. Towards your right side, there is a close. If you close that part, the screen would look a little bigger, sir. I think so. This part,
Well,
yeah.
Sir, please once check in view option, sir. Like full screen.
yeah, it is okay.
Yeah, it's
not
better
really
than
visible,
earlier
sir.
answers. Still, I think we can.
In view option, once check it, sir.
Huh?
View option above top. File edit view
View, then full screen mode.
full screen mode.
Yeah, yes, sir.
But actually,
Yes, sir.
I just thought that I should go with that writing mode also in PDF because of some doubts. Huh? I should go to that, would have been better. Okay, anyway.
Sir, you can escape that time. Then you.
Okay. Just a minute. Hey, আমি একটু বাইরে lecture আছি। Okay, anyway, the topic is modeling and control of switch mode power converter. Why the modeling term is coming, you know, in control, modeling is closely, that is inevitable. For any system, whether it is a power electronic system or any system, you must go through modeling, mathematical modeling, because mathematical modeling is the first step for analysis and design of any control system. Okay. Now this modeling, you know, in linear control theory, either you go for transfer function modeling or you can go for the transfer function, that this vector matrix form, okay? And you can go for nonlinear modeling also using nonlinear equations. But as I told you earlier, that my topic is mostly relates to that linear control theory. That's why we should need that linear modeling of the power electronics converter. Okay. So next is the introduction, then switch mode power converter, control requirements. Why you should go control requirements again? In power electronics converters, unlike other systems, you should know the circuit concept, okay? Because many power electronics engineers, I know that they are unbothered about the designing of control system. Yeah, they know the only control of open loop and closed loop control, and know how to sense the voltage, current, and then take the feedback, and then accordingly they can run the system. And frankly speaking, they are not taking the concept of control system design, either say design of Ziegler-Nichols or PID tuning, or frequency domain technique, or your root locus technique in time domain or in frequency domain, or PI controller or PID controller. They are simply putting the structure of PI or PID controller or functional controller. Then they are controlling that their system. You may ask, then system performance, system may be stabilized. Yes, they are doing all this thing in practice, in trial and error. My students are also working, when Dr. Minal also is my student, when he worked on levitation system, there I told him that how to design all these things, because he knows also better that even without designing some system which is not unstable system, they may run like motor control system without designing of all these things. Okay, but some critical system like magnetic levitation system, unstable system, until unless you design correctly with with your control system. That's why I must tell, because I have worked on control system as well as in power electronics, so I know better that how control system is related to your power electronic system and vice versa. Okay, so that control requirements and technique first we will take, and then we'll tell about the modeling of converters, then design and implementation of type 2, type 3 converters. I just want to tell about this thing, because power electronics converter particularly, again, there is a change in structure because of its inherent in nature of this type controller, type 2 and particularly type 3 controller. Okay, this I have seen over the years. I have worked on this, and I have seen that this controller perform better than normal PID structure. Huh? Okay, so this is, you may treat that this is a special type of controller particularly used for electronics converter. Okay, so there is a special importance of this type controller. Then closed loop control concept, and then their implementation, how to implement these things all in closed loop. That is also very important, because majority system will run in closed loop. I don't know how many you are working in hands-on practice on this closed loop control of your converter, because many project I find in BTech level, either they are making one inverter or they are making in converter. Even they do in practice, but things are not running in closed loop or in applications. Okay, so until unless you do that total thing in closed loop with the applications, that your learning of designing all this concept is not be completed. Okay, and design and implementation of some improved DC-DC converter. Why I have taken this thing? Because I have seen that there are a lot of limitations of this DC-DC boost and buck boost converter. So that's why there are some modifications, and these modifications are unique in nature, because these some configuration, some topologies, okay, that done by our research team in our laboratory, they have already published in IEEE, and some of them are already being patented. That means this improved configuration now in literature, and you can go through it, and you can also apply in your applications like battery charging, EV charging, and particularly solar applications. Okay, and then if time permits, I will go a little bit about bidirectional converter, because when you talk about the converter, particularly these battery applications and fuel cell and DC microgrid, or your solar applications, okay, there we need the converter must act as bidirectional mode, because sometimes you have to charge the battery, and sometimes you need the output from all this battery and fuel cell to supply the power to the load side or grid side. Then multi-level or inverter, I think I cannot cover at this stage, because maybe if time permits, I will just show the slides. Okay. Now, yeah, is it visible? Something.
Yes, sir. Yes, sir.
This part is okay. Now, very first diagram shows the configuration of basic block diagram of any power electronic system, where you see the power converter, that is the heart of the overall power electronic system. As I told you, that it may be any form, whether that all depends on that what is the input power and what is the requirement of your power at the load side. Okay. So based on this, you have to design this power electronics converter. Now, output you have to sense in closed loop control. You may ask that in open loop also there are many applications. Yes, like in open loop control system, you can using that converter, you can run many systems. Okay, but if you want to use perfectly that concept of control in closed loop is inevitable, and you must run the system in closed loop. So you have to sense the voltage or current or other parameters and compare with reference, and then controller will generate the control signals as per your load requirement. Okay. Now, while coming to any converter, you must know that earlier we used to have that the linear power converter, means that you have to use the device, whether it is a MOSFET or IGBT or BJT. But earlier, if you see the revolution, that earlier we used to work on transistor. If you see the transistor family, earlier we used to have transistor, no? So transistor in that time, for high power applications, majority applications was in linear mode. Even if you see that today's power supply, you must go through that for high rated power supply, all the linear power supply in your laboratory, whether you are working. Okay. So there you see the basic things looks like this. This is the structure of this linear power supply, and to appreciate the advantages of these of the switch mode power converter that I will focus mostly, it is desirable first to consider the linear power supply. Here, in the linear power supply, it is mandatory that you must go through that linear line frequency transformer, and then the power has to be rectified by means of that either uncontrolled rectifier or control rectifier. Then after filtering, you are giving this power to this, and you are sensing the voltage compared with reference, and then you are controlling the base current, and so that the switch, the device, the transistor will act as a switch act as in active region. So so what is the problem here? The problem is you are using the low frequency transformer. Such transformer are larger in size and weight compared to high frequency transformer, and the transistor, as I told you, that operates in active region, incurring a significant amount of power, and that's why there are considerable amount of losses. So therefore, the overall efficiencies of this converter are in the range of 30 to 60%, not beyond 60. Or nowadays, if you just replace some components or that modern devices of transistor like MOSFET, IGBT, it may go to around maximum 70%, but not beyond that. Beyond that, so very poor efficiency, and it will have a larger weight and size. On the positive side, okay, this power supply will utilize simple circuitry, so control is easier, and cost is also less. With a simple analog control, you can implement this linear power converter, and it will not produce large EMI. EMI means electromagnetic interference, that is arising out due to that high rate of change of voltage, DVDT, or DIDT, rate of change of current across the switch and across the your that circuit region. Okay, but that may not be the case in switch mode power converter. Here there is another diagram we just follow. This is the output of this filter capacitor. So here there is one design concept that you have to select the trans ratio, because you see the that use of this transformer. Here this transformer not only isolate, okay, it will that one purpose is it will isolate from this primary side and secondary side, and there is another one that you should follow the trans ratio, because because of power conversion you need to have that change of trans ratio. Okay, but you just select the trans ratio such that here this VD minimum, the output here, should be greater than that output or VO, voltage VO, but it should not vary by a large margin. Then what will happen? The difference will come here across the transistor, and since transistor is all time on, so that voltage multiplied by that current, okay, will be the losses, and that will be considerably high. Now, it is clear that you have to go for switch mode power converter. So whatever may be the applications, you should use that device, whether it is a transistor, MOSFET, IGBT, thyristor, all these, you must use that as switch. Switch means either it will be completely on or completely off. Here you just see the two diagram of family that very familiar to you, that like buck converter. Okay, this is in non-isolated mode, and this is in isolated mode, just using of high frequency transformer. Okay, since it is used operate as a switch, so by avoiding their operation in their active region, so a significant reduction of power losses is achieved, and this results a high energy efficiency, maybe 80 to 90%. And as I told you, with some modifications, like using the switch as soft switch converter and replacing this MOSFET, these diodes by device like MOSFET, and operating in synchronous synchronous operation. Okay, then you can achieve that more than 90%. Okay, the efficiency is very, very important while talking about this power flow. So large power handling capability, that is another advantage, and small weight and size, because of this high frequency transformer. As the operating frequency increases, all the component size reduces, right? So here all the components like inductor, capacitor, transformer, all the size will reduce, as the operating frequency is very high, and you know what should be the switching frequency. These are all basic and related to your converter design. Nowadays, switching frequency, we mostly operate more than 40 kilohertz to say 200 kilohertz for our laboratory applications. But you know, MOSFET nowadays can go to up to say megahertz level. But anyway, majority applications for power conversion, we are using maybe 200 kilohertz or maximum maybe 400 kilohertz. So you just imagine that what should be the size of this component. Component size will be reduces, and nowadays you know all the devices. That is another important thing. There are a lot of research is going on to replace our silicon carbide devices that is mostly used nowadays. Okay, by wideband gap devices like your gallium nitride devices or silicon devices. Okay, so that devices again operate at very high frequency, right? So all these things are coming and already are in use in some applications. Okay, so there are other advantages. Multiple output you can easily connect. That's a lot of secondaries in the secondary side depending on the coupling of primary. Okay, that I will show in other applications. But at the same time, these converters are more complex, definitely. Okay, and EMI problem particularly is very much stringent. So EMI, because this switch will is on and off at very high frequency. Okay, so that will give rise to very fast rise of dB voltage and current, very high rise of DVDT and DIDT. Oh, that will create EMI, electromagnetic interference. That is again a problem in design. So you have to take care about all the design means your prototype, particularly design in PCB, printed circuit board. That you have to take care while working on the switch mode converter. And some converters may have some stability problem, as I told you, that particularly DC-DC converter either in the form of boost or buck boost mode, other than buck mode. So that is mostly used because majority applications you will go through that. You have to boost up the voltage. Okay, and for that you will find that some problems in their structure, and because of that that converter may have some stability problem, and you have to take care all this thing in control. Okay, and also that some cases you will find that their bandwidth also restricted. Okay, poor dynamic response. So you have to work with your converter, your control, so that you can achieve a better bandwidth, and also you can achieve that better your dynamic performance. Okay, so that PWM control everybody knows. So you know that switch has to operate based on this control logic, where you will find that your actual voltage is compared. Say in case of power supply, then V control is there. V control is that the error signal. But normally in your power control book, it is there that it is directly compared with this repetitive kind of signal, and it is generating that duty cycle. Okay, but here we will try to modify, because that control signal, it must go through some control logic like PID or type controller. Okay, so that your control signal will be modified and it will give the desired output. And here the logic is this, that as long as your B control is greater than your triangular or sawtooth waveform, it will give that output. Output will be high, otherwise it will be low. Okay, so that accordingly you will get the output voltage pattern like this. But there is a problem of this kind of voltage output pattern for some applications like computer power supply or say TV electronics power supply. So we have to avoid this. And in majority cases, you will find that load is inductive in nature. So that is another problem, because it will, when the switch is on, that load will, that inductance will store energy in the form of Li square, and when the switch is off, then then it will, that reactive power, that voltage stress will come across the switch. So you must provide a path, and that's why you know that very familiar and important buck converter has developed by putting that LC, which will contribute a second order filter at the load side, and this diode which will provide that flow of that, what we can usually see that that your that for your flowing the current. Now I will not go in details, but I will tell some practical idea that about the selection of switch and about the selection of that inductor, all the components here. Because of this excellent filtering capability, you know that the selection of this capacitor is not that much stringent like boost or buck boost converter. Okay, because the what we call ripple current will flow through the capacitor, and the ripple voltage will be this ripple current multiplied by ESR, equivalent series resistor. Okay, so you must specify while purchasing the capacitor not only the in terms of microfarad or farad or a voltage rating, equally important. And another important specification is ESR, equivalent series resistor, right? And in this case, since that delta I ripple current is not much, that's why your delta, you should not bothered about that, is because if you want to purchase a capacitor where with low ESR value, then the cost of the capacitor will be high. Okay, right? So these are all voltage that inductor voltage and current waveform. Because of this excellent filtering capability and because of its structure, that buck converter always prefers to operate in continuous conduction mode. You know the mode of operation, continuous conduction mode as well as discontinuous conduction mode. Here you just see when that if the load of the buck converter or any converter is slowly reduced, this load, okay, then eventually it will that this minimum current will just will be zero, and if the load is reduced still further, the inductor current will be zero for a period like this, and it will operate in discontinuous mode. So usually all these basic application concept at the boundary level, boundary condition, like that condition, what is the current is just output voltage divided by resistance, and that is limit, and that is equated that with the delta I by 2. And from this you can find out the value of inductor. And since I am telling that it should prefer the continuous conduction mode, so this design of inductor you should take from this empirical relationship here. This value of inductor should be greater than the half RT1 minus D. So you know what is your switching frequency, what is the load. Accordingly, you select your inductance. So you have to select inductance first, and then capacitance, and then capacitance selections. From this diagram here, this change of charge of the output capacitor that is represented by this shaded area, and that can be find out from the angle criteria. that triangle concept delta Q and this thing, and from that you can find out the value of capacitance. Okay, and after selecting that value of inductor, you can select the value of capacitance. Okay, and there is another thing that is related, that is what should be the, because it will act like a second order filter, so the cutoff frequency of the filter that should be much less than the switching frequency. Suppose if you select the switching frequency is 40 kilohertz, so this should be at least 10 times less than your that switching frequency. So accordingly, there is another correlation that is not there in the slide, but anyway, that you also should take care while designing. So what I want to tell here also, that in one trial you cannot find the exact value of inductor and capacitor. You should take the primarily from that empirical relation, that what is that inductor value, then capacitor value, then go for that relation with cutoff frequency, and there it is related to switching frequency and cutoff frequency. How it is related, you just see that ultimately you have to that you should have the ripple, yeah, ripple voltage much less. That is also be specified, that what should be the ripple voltage. Okay, so accordingly you have to specify, you have to design all these things. And for discontinuous mode of operation, this is the equation. Though I told you that it will be always prefer that buck converter, because you should take the advantage of the position of this L and C and excellent filtering capability. Okay, so that's why it is very useful, that buck converter topology in many applications. Buck converter has relatively smaller ripple value, and closed loop response is also better, and there is no such problem like RSP0 that is usually you will find while going through modeling of boost and buck boost converter. This is once again, I will not describe in detail, but some design concept of that inductor capacitor and selection of the switch. Here you just see it is not like buck converter. Here during on time, that current, what we call that inrush current. Okay, inrush current is only limited by this inductor. So here you have to take care this about the selection of this switch. So this switch should have much that have should withstand that much current stress due to that inrush current. Okay, and the other important thing is this boost converter or buck boost converter. You should always connect by load while preparing the power converter and while giving the supply. Okay, because of this capacitor. Otherwise, this capacitor will be damaged. And here you see in the secondary side there is no inductor, so obviously that ripple current will be much more, and the selection of this capacitor is more stringent, because as I told you that ESR value here you should select much smaller than your buck converter. Of course, if you compare with the power rating, voltage rating, and all these things. Okay, so switch has to handle high inrush current, and here later on you will find that you will get one RSP0 right up pole 0 of this here. So this converter will be non-minimum phase system. That is again control what is non-minimum phase system, because of this presence of right up plane 0 of this boost or buck boost converter while doing the transfer function output to control transfer function. That will come later on. Okay, and because of that, it is preferred to operate in discontinuous mode of operation, and while operating you can avoid, and that also can be seen while going through the modeling, either discontinuous mode or tri-state mode. Then boost and buck boost converter will not have that right up plane 0, and then control will be easier, and then you can easily control. Even with PI control you can control in closed loop. Okay, so these are all the basic circuit, the basic equations. I'm not going through this. So at the boundary condition, So here it is written for continuous mode of operation, but as I told you, you must operate preferably in discontinuous mode of operation. So these inductance should be less than this half R T d1 minus d square, which is derived from the basic that boundary condition. Okay, and for discontinuous mode of operation, this is the voltage and in output voltage and input voltage ratio. Here you see whatever be your delta 1, it is delta 1 plus d is always greater than this delta 1. So in spite of its operation, so here other thing is important, not only during on condition of the switch, but also during discontinuous mode of operation, that output current, output power will be supplied by the capacitor. So this capacitor, okay, is a very, very means important one. You cannot select anything like just trial and error method. Okay, you have to select the value of this capacitor with low ESR value, and of course rating should be that depending on that output voltage rating, as well as you have to consider all these things. Okay, so relatively more ripple current at the output, as I told you. Closed loop response is poor because of that right upper zero, and in discontinuous mode the effect of non-minimum phase vanishes. That's why we prefer mode of operation of this boost converter is discontinuous mode, similar to boost converter. Here also inductor in the primary side, but see the inductor is connected across the supply, but that in boost converter it was in series with the supply. So I am just always sometimes giving my students, particularly BTech students or MTech students, that for equal power rating, what should be the value means of this inductor? If you compare with a equal power boost or buck boost converter, here you see since the inductor in parallel, okay, and in boost converter it is in series. So while turn off of the switch, here not only the input supply but also the inductor will transfer energy to the load side, and but that is not the case in case of buck boost converter. So inductor requirement as well as side in case of boost converter should be less than buck boost converter. Okay, that is very important. And here output voltage polarity is opposite and all these things. And here also you should take care about the current stress rating of while selecting the switch. It is also like boost converter. Okay, and you have to operate here again that your converter in discontinuous mode. That's why this inductor here it is written for continuous mode of operation, but that should be less than of this one. Okay, and capacitor selection is because your capacitor, the load current will be supplied by the filter capacitor. So during off conditions, on condition, so from these equations you can find out the value of capacitor. So once again, after designing and all these things, in one trial it is not possible. You have to go through all these fundamental equations and you have to see through simulation study as well as in practice. Okay, that you have to measure in oscilloscope that how much your ripple is, what is your efficiency with the duty cycle, with the load. Then finally, with the closed loop, of course, you have to see the performance. So when you talk about this, your performance of this converter, so that is not only relates with the design of controller, but also design of these power system components, these power electronics components, switch, selection of inductor, active component, passive components. Okay, so this is the familiar Chuk converter. Here again, you just see this selection of, here you just see once a, though you know, but you see the position of inductor at the secondary side as well as primary side. So it is getting advantage both way, like boost converter as well as buck converter. But only that capacitor here, this capacitor has to be relatively large, means compared to boost and buck boost converter. And because it is not only supply that voltage, it will not only supply this A, but you have to handle capable of high RMS current, so low ESR is essential. Okay, and from that you see that when switch is on, the pattern of inductor voltage of 1 and 2 is like this, and during on period both the inductor will be charged, and these are the equivalent circuit diagram. Okay, and from this you can find out the input output relation, and it is similar to your buck boost converter. All right, so here again you will find that because of the presence of that inductor in the primary side, okay, you will find that RHV 0, right up and 0, so you have to preferably operate in discontinuous conduction mode. Other switching converters, these are very much useful for different applications, particularly when all these basic converters will operate in isolated mode of operations. So these all looks like edge bridge. Now there are specific names. This is called asymmetrical edge bridge converter in many applications, and I find because here only 2 switches and 2 diodes are used, right? It requires only the half number of switches and diode than full bridge topology. But only problem is that it can operate only what we call that quadrant of operation, either first quadrant or fourth quadrant. But it can give that output voltage with this ratio 2D minus 1 into BS. So maintaining the duty cycle, the output input relationship may be linear one. Okay, this is half bridge topology compared to the four switches. Here just 2 switches are replaced by 2 capacitor. This power amplifier has the disadvantage of derating of supply, utilizing half the value of its value anytime, and the compared to this edge bridge asymmetrical bridge topology, here it can be possible to operate in 4 quadrant mode of operation. Why it is required? Because in many applications, like suppose DC drive applications, sometimes you have to operate, particularly in the applications of electrical vehicle. You have to operate sometimes in motor mode, sometimes reverse motor, sometimes generator, sometimes reverse. So there you have to operate in all 4 quadrant operation mode of operation, and this is possible because here you see when this switch is on, the current flow like this, and here polarity across this load reverses, as well as current is also bidirectional, because when the switch is off, the current will flow, this capacitor, current will flow through this diode. But when this switch is on, current is bidirectional, but that is not the case in asymmetrical bridge converter. But the only problem is that you have to take care about the balancing of this charge of this capacitor, either through the improved modulation technique or some additional circuitry you have to apply along with that your controller circuit, so that the voltage it should be balanced. Suppose if you apply VS here, normally in theory you know that it will be, if you have equal amount of capacitor, then it should be balanced VS by 2 and VS by 2, but practically it is really difficult. But you need to have, because it is mandatory in some applications, Otherwise, you know that you can't maintain the equal volts second relationship. I will come while talking about the isolated mode of converter. Or if you want to use like in inverter, there also you will find that there will be level shifting. And because of that, you know, the TSD level also will be reduced. Okay. So if effectively if you see that only you will find that across the load it will all means if it is not balanced, then only DC current will flow through the load. So if you use the transformer in case of isolated converter, there will be problem of saturation. So you have to avoid that one by taking care with that additional circuitry to balance the capacitor voltage. Okay. Now in full bridge, as I told you, the circuit has of course better properties such as faster dynamics with a smaller current ripple. Under the same DC voltage conditions, 4-quadrant mode of operations are possible, but it is at the same time, it is a complex because you have to use 4 switches. So 4 gate drivers and associated circuitry. Now I find in many applications single switch based converter, and I have also used these as novel topology in my project work, where you find that when the switch is on, the voltage across the coil or load, it is positive, and you are using here that one inductor and capacitor in parallel with this diode combination. That means when the switch was on, this diode was reverse bias, capacitor was trying to discharge to this resistor, and when the switch is off, then this diode will be forward bias, and this voltage across the capacitor in steady state will come across this coil or load. So with the predetermined parameters of this resistance and capacitor, it is possible to apply the equal amount of the source voltage across the coil or load. So so you can the voltage across the load, it is possible to follow the same gain 2D minus 1 like H bridge, that asymmetrical H bridge converter circuit. Okay. So it uses only one switch and one diode in contrast to 2 switches and 2 diode of the asymmetrical bridge circuit. So there is no need for gate drive isolation. So there will also be less EMI, but only problem of this that you are using this resistor, so the circuit will be little bit lossy, and in terms of energy efficiency, it will be not good like symmetrical bridge or full bridge converter topology. Here, other advantage is that for low power applications, of course, you can extend these switches. This means just using another switches and using same dumb capacitor and resistor, just like this. Okay, and you can switch on at same time all the MOSFET or IGBT, so that at the same instant you will get the voltage across this, and this is very useful. I find particularly some applications like multi-coil based maglev system or SRM motor control or stepper motor control. Okay, that is normally SRM motor you will find that use of in electrical vehicle, and stepper motor control for some control applications. So this type of topology is very useful. This power circuit topology can easily be extended to multi-coil system like this, such that the gate drive signal may not need ohmic isolation. Moreover, all amplifier may share common energy term capacitor and resistor. But at the same time, as I told you, the circuit is not energy efficient, and it is less stable than H bridge, normal H bridge power supply. Moreover, the circuit produces more current ripple and lesser bandwidth. If you go through some analysis, even in simulation, you will find that kind of result that ripple current and as well as in terms of bandwidth while going through the frequency response of all this converter that you can easily do even in MATLAB. So these are all isolated switch mode power supply. It is modified with this using high frequency transformer, and circuit looks like this. The usual buck converter is modified. There are so many advantages. The output is electrically isolated from the input. Output voltage can be varied with trans ratio because you know normal buck, boost, and all this converter can transform not more than 10 times either buck side or boost side. So by using this transformer and you just varying the trans ratio, you can vary widely. The polarity and step up, step down restriction of this converter no longer apply because you can change the polarity by using this secondary and using the dot convention. Those who are familiar with how can you that all things are practical, you can do until unless you can do this in laboratory, you cannot find the actual practical idea. Okay. The introduction of course, a multiple output also possible. Usually you are using multiple outputs in case of isolated mode of converter. The introduction of a transformer, of course, will add size and weight of the SNPS and introduces further losses, either eddy current or hysteresis losses. So that also can be taken care because there are a number of advantages which outnumber the disadvantages like this. So you can always work on this and you can compensate. And as a result, we are using that forward converter like this. And as I told you, that when you are using like this and primary side, it is always either the voltage getting either more than zero or zero or more than zero. So if you take that average current following through the core, the primary, it is always a DC kind of thing. So there is a chance of saturation. So you have to demagnetize. There are many options, either using this tertiary winding, one third winding you just see here, and see the polarity and all these things. I'm not able to go through details, but anyway, you just see when switch is off, this tertiary winding will provide negative voltage. If the trans ratio are similar, then equal amount of negative voltage that is required, but that is not mandatory because your duty cycle may also be changed. It is not that it should operate 50% duty cycle. Generally, it operates 50% duty cycle, but it can be there is a change of trans ratio. So how can you maintain then volt second relationship? Volt second relationship you can maintain that by operating that not more than 50% duty cycle. Okay. So here all the application like buck converter, as I told you, the low current ripple does not place heavy duty on the filter capacitor, and it should operate in continuous conduction mode. And you should design inductor capacitor only. You have to take care about the trans ratio that will come into play while changing, while transferring, primary side to secondary side. You have to take care. Other basic formulations will be similar. Here transformer utilization is poor because you are using only one half. During uptime also you have to modify. So normally used in continuous conduction mode, suitable for 500 watt. And for better efficiency, as I told you, that this diode may be replaced by MOSFET, and then it is possible to operate in synchronous rectifier mode because you know the diode drop is considered 0.7, 0.8 volt, and diode is some way that due to the reverse recovery power loss, some amount of power loss, considerable amount of power loss is there. That can be compensated by if you use replace this and then efficiency will be a little bit better. You can also avoid the saturation by means of, as I told you before, that by placing asymmetrical bridge converter, edge bridge converter in the primary side. So there equal amount of positive as well as negative voltage you can apply in the primary side. So separate demagnetizing winding are not required. You can also enhance the power by combining parallel converters. Later on, you will find this paralleling concept of converter will lead to the interleaving technique, and that is also bit shown in the later part of my slide. This is the half bridge kind of topology. Here also you see the primary side is replaced by edge bridge using two capacitor and two switches, and secondary side is used the center lead transformer. So in both half we can utilize when the switch T1 is used, the upper part is utilized, and when T2 is used, this part is utilized. So transformer utilization is much better than single switch based converter. Here also duty cycle, it is not be restricted to 50%. You can also use more than that. But anyway, normally you can use 50% because of that equal volt second relationship. And this capacitor, that is another advantage, that it will block the DC component of the transformer, so to avoid the saturation. So these are all voltage and that current relationship. From that, you can find the DC gain, and you just see the DC gain is related to that not only the duty cycle but also the turns ratio. Okay, so you have to judicially select the turns ratio. Here, two transistors are connected in series, so these are you have to need isolated power supply and power rating 500 to 2000 watt. You can utilize for a single power supply. Of course, if you want to increase the rating, you can always connect in parallel. This is the full bridge converter topology. Here, the primary side is replaced by four switches, as you see, and all four quadrant mode operation is possible. Here, not only the current, the voltage across this primary is bidirectional, but current flowing through this is also bidirectional. So all the four quadrant mode operation is possible. Obviously, the output power for equal switches, rated switches, is double than the half bridge with equally rated transistor, and the gain you just see it is 2 times that gain that you have obtained in half bridge converter. But of course, two extra transistors are required. So control circuit is complex. And here, if we put one capacitor, so that will also be helpful, and it will block the DC component. So all these things will be taken care while going through the design. These are all I am talking about, not control, but power electronics, because fundamentally, before going to the applications of control, you must clear about the power electronics, because these are all correlated. Unless your power electronics components are clear, okay, because it will just give the amount of ripple, amount of that your phase lag, L and C and all these things. Okay, so unless if you correctly design the power electronics part, then your design of control will be easier. Otherwise, that will be much load on control system design. There will be much you have to take care of that extra precaution in control design. It is like push-pull converter topology. Here, these two switches are in common source configuration. So here you just see, if you just compare with a full bridge topology, here not only secondary is interleaved, but primary is also central lead transformer. But that is the problem, only problem of push-pull converter, because you have to must see this primary voltage balance in these two sides. It must balance. Otherwise, what will happen if each switch should not conducted the exactly equal period, then volt second products across the two primary will be different, and then there will be the flux imbalances, and due to that your power supply, particularly the switch, will damage. Okay, and majority failure of this possible power amplifier is due to this flux imbalance in the primary side, so that you have to take care. Okay, otherwise that equal gain is possible like the full bridge topology, it is efficient and compact, and two switches can be driven from the same power supply because it is in common source configuration. So switches need to have a voltage rating. Switches can be controlled from common reference voltage. Transformer utilization is also much better than forward converter. But another thing is switch rating, the voltage rating is double, because when switch is off, you just see that whatever voltage is there, that will be added with another voltage here in the this side. So this voltage trace will come double of the input supply voltage, but that was not there in case of full bridge converter topology. So these are all merits and demerits of this all converter. All these converters are derived from basic buck converter, but equally at the same time you can also derive from the basic boost as well as buck boost converter. Here the topology of flyback converter, which is again very similar like buck boost converter, but only thing you have to take care about this design of this. It looks like this normal transformer like this one, but it is not a normal transformer. It will be inductor transformer, because when the switch is on, considering that your energy, you have to store energy in the primary. But you know that if it is ideal transformer cannot store energy. It will only transfer the energy from primary side to secondary side. So you have to take care about the design, this one component, which is inductor with the secondary winding. Okay. And if you go through the basic formulation from this this waveform diagram, then you can find out the primary side inductance, which is related to n squared tribe because of this trans ratio. Okay, more commonly used in discontinuous mode. Other things all are there from that basic buck-boost converter. But at the same time, it is very, very attractive, because you know isolated mode of operation is required because of many advantages of power electronic circuit. Okay. So there, particularly, you know, majority applications of that electronic power supply, that computer power supply is that flyback converter topology. All right. But at the same time, high peak transistor current, larger filter capacitor with low ESR, that is again essential. So you have to take care while selecting the all components. One design example, the input voltage is specified 300 volt plus minus, and output voltage is 5 volts. So you have to step down such a high value of voltage from say maximum voltage of 330 volt to 5 volt. So it is not possible using normal buck converter. So you have to use the isolated mode of converter. All right. And here again you see the rating maximum current at the secondary side is 30 ampere. So 30 into 5 means 150 watt, such a small wattage. So only this single switch based topology is essential, is sufficient. But if your power rating is much more, say if it is more than 500 watt or something, then you have to definitely take care about all this full bridge converter or this half bridge converter topology or push-pull converter topology. Okay. So here, using basic formulation, you know that how output input voltage relationship is there. So from the basic formula, you can find out the trans ratio. So trans ratio selection of transformer, you have to select like this, and then you have to go for the selection of design of inductor from the basic here formula, empirical relationship of RTD1 minus D. So where you have to go for the D minimum and R maximum, because your inductor should be always higher side, so that you should go for the design of R max as well as D min. Okay, so after putting all this value, you just see that inductor value is 5.3 microhenry. Okay, so after multiplying with the factor of safety, you know, at least 2.5 times of whatever you have designed, so inductor comes to that value. After designing inductor, you can put this value in a capacitor selection. So capacitor is 79 microfarad. So you just see how much ripple current is there, because you have to select while selecting capacitor the ESI value. So ESI value is calculated after seeing the ripple current, and of course you have to select your transistor, what is the voltage trace as well as what is the current trace. That accordingly you have to select like this 2 into VI max, as well as what is the current flowing to the primary, that you have to see like this. You have to convert the current of secondary into the primary by turns ratio, multiplying the turns ratio. So accordingly you have to select all the switches. So the components like LC, diode, transistor, and the transformer. So everything you can select from this design concept, and it is valid for other converter design also. Right. Now I am slowly entering into the control. Right. Control requirements and techniques. So firstly, I will just tell the concept of the different closed loop control from the circuit point of view. That converter you should design such that you must maintain good line regulation. Line regulation means here, even though there is a fluctuations of line voltage, but your output voltage should maintain constant. You must have good load regulations. Good load regulation means even there is a fluctuations of load current. Your output voltage should maintain constant. It must have good transient as well as steady state performance. Even there is a fluctuation of load, you will find that temporarily your output voltage there will be some changes, but it should immediately follow the steady state. Means that your nominal output voltage, and it should be stable under all operating condition. Even though I have shown this design example, you just see here that even though there is a fluctuation of current 3 ampere to 30 ampere, okay, your output voltage is to be maintained constant to 5 volt. But here, while doing all these components, design of this component, there is no need to go for the closed loop thing. Only open loop means from the basic, because you need all this basic formulation, okay, and that is comes from the circuit operation, okay. But it is not possible, even there is a fluctuation of load, it cannot possible to maintain the output voltage constant. So for that, closed loop control is required, and for that you will just see that kind of requirement like this. This is a voltage mode control. So there are 2-3 control techniques are there in power electronics and closed loop control. You have to sense the output voltage, okay, and compare with reference, then passing through error amplifier. So normally here it has to pass through this control signal, pass through that your control block. But for the timing, only just concept of load regulation, line regulation, how it will be maintained, that you have to make clear. Here you just see, even there is a fluctuation of output voltage, so VO changes, then you just see your control signal will change accordingly. It will either go up or down, and accordingly your duty cycle will be maintained constant. So that's why it is called direct duty ratio control. And in most power supplies, switch mode power converter or normal power converter, it will be applicable. It is simple and reliable. Load regulation is good, because if there is a fluctuation of load, that output voltage immediately it will be uh, regulated. But if there is a fluctuation, sudden fluctuation, of input voltage, immediately it cannot be taken care. It can be taken care within few cycles, but by that time your output voltage may go drastically high value. Okay, so line regulation is poor, and other thing is transient response is also better because of that topology of this buck converter. Okay, but you have to utilize boost converter or buck boost converter for majority applications. So for that, transient response may not be better using direct duty ratio control. Okay, so what is called voltage feed forward control, that the problem of line regulation that was there in direct duty ratio control, it has been rectified here by sensing the input voltage, and you just see it has to pass through sawtooth generator, and the height of the sawtooth generator is increasing with the change of increasing voltage. So accordingly, this control signal, what is coming from the output side, that may remain fixed, but with the change of the height of that carrier signal, you just see the duty cycle immediately controlled. Okay, and from the mathematics also, you just see output is no longer dependent on the input voltage, because output is only proportional to the control voltage. So both line and load regulation is maintained uh, good, and closed loop response will also be better. And that is again current mode control. Majority PWM chip, whatever be the applications of power electronics converter, either DC to DC, DC to AC, AC to DC, you will find that using current mode control. Okay, current mode control, this is the usual structure you just see here. Here, not only you are sensing voltage, but you have to see the current in the inner loop. Okay, so it is basically two mode control, outer voltage loop control and inner current mode control. And you see the logic here, the clock pulse is generated by this clock, and when this clock sends the signal like this, your RS you are taking, you have to take the help of latch, RS flip flop or latch, just to pass through that. Now, as soon as the input is high, the output of the latch RS flip flop is high, so the transistor will be on, and your inductor current, this is the output pattern of inductor current. So the current is sensing here BS here, so it should increase like this, and when it catch to the control signal BC here, then the output will be here, the reset pulse output will be high, so reset pulse will be generated like this. So as soon as reset is high here, your latch output will be low, so that your effectively you are getting the transistor or MOSFET drive or get pulse is like this pattern. Okay, so how voltage, that line and load regulation is maintained, you just see here from this equation. When output voltage decreases, VO is decreases, then VI minus VO, this is going to increase. That means rate of change of current will try to increase very fast, so it will catch like this, so your reset pulse will comes fast, so your on time will be reduces. So if output voltage reduces, on time reduces, that means your output voltage will be regulated very fast. Okay, again you can find out other way that how line regulation is maintained, because you are sensing this current here, and if your line current, suppose VI is more, then VI minus VO, that will be faster, so it will again, the reset pulse will be generated fast, so your the width of the on time, means on time will decrease, that means your duty ratio is decreasing, so your input voltage increasing and duty cycle, so that output voltage will maintain constant. So both the line and load regulation is maintained is excellent. Closed loop transient response will be better current limit protection, because you just can put simply a Zener here at the reference side, and you can implement the pole protection, current limit protection, and it removes one pole because that time constant, magnet time constant, you can bypass just because you are using. See, I am coming to this circuit here now. Yeah, from that it will be better to explain. In voltage mode control, you just see it was just only one single loop control, and there you have to find out, if you find out output to control transfer function, there the magnet transfer function was included. But if you take the inner current loop as well as outer voltage loop, then the inner, this side, you have to take care about the magnet time constant. Okay. So while designing here, of course, as I am telling you, this is taken from a standard book of that Nedmon, but they have simply bothered about that design of controller. Like here, it has to pass through, as I told you, it has to pass through the controller block, either PID controller or type controller. Here also, there will be two controller. One is current controller. Now, current controller may be a simple PI controller in this case, or even maybe proportional control will be sufficient. But it is always better to use PI controller because to remove the steady state part. Because in current mode control, one definite problem is that to maintain the steady state error, the accuracy. Okay, so that we should always use that PI control here. And output side, the voltage control you must use as a PID or type control that will be described later on. Okay, but from this concept, at least the idea is clear that while going through current mode control, you must take care about the design of both current controller as well as voltage controller. Now, while designing the current controller design, current controller bandwidth is much faster than the voltage controller. Okay, so at least 10 times faster than the output voltage control. So all this idea will be utilized while designing the controller. So this is there. Okay, so up to this, what I have described, three different mode of control. One is direct duty ratio control, another is voltage feed forward control, another is current mode control. And I told you that majority for simpler applications, you will find that voltage mode control or direct duty ratio control. And in if you want to go for means better control, means you should always have, because you are taking care about the current sensing. So one current sensor is required other than your voltage sensor. So circuit in terms of cost, okay, and complexity, definitely it will be much more than your voltage mode control. But at the same time, it is very means general concept that while using all this complexity and better sensor as well as better control, then definitely your control will be much better, because we are talking about here control. So if you want to control much better way of converters, then definitely current mode control you should select, you should utilize, then voltage mode control. Okay, is it clear? I am not getting any feedback. Any response from participants? If you have any doubt up to this, you may ask. Yeah. Or if it is clear, then it is fine. I can proceed, because only half an hour I find left. So as I told you, so up to this, the idea, even those who knows something about power electronics, something about simulation, using say MATLAB or PCM or PSpice, they can easily simulate from the basic fundamental concept of designing of inductor, capacitor, selection of switch, selection of turns ratio of this transformer, design of transformer, design of magnetics, all are required. All are required, all are important. You can't omit any part. Okay. So if you know all these things, then up to this you can achieve. Now, after this, actually you will face lot of difficulties, because so far you have an idea that if you know the components, if you know the design of power electronics, if you know the fabrications, if you know the simulation, then obviously you can achieve up to this for any converter. Say you start with buck converter or boost converter, you have fabricated in PCB, you have simulated accordingly, you have formulated all the things, and you have running the converter. Now you will face the actual problem. Can you tell me why? Can you tell me, any of you, why? Any response? Otherwise, it will be useless, because so far I have spent 1.5 hour time. I told several times what is missing here. Who can tell me?
The controller, sir.
Controller is missing here. Yes. Who is telling?
Anil, sir. Yes, sir.
Anil. But I should expect from participants. There are many participants from various parts of our country, and the main objective of this ATAL program, what I find, that it is not like a webinar or a seminar. It is like a training, and it will be always good to give the input in terms of that practical session also. The idea of this ATAL FDP program sponsored by this AICT is that it is not only that it is not only that to give a demonstration kind of lecture on theory, but also lecture on practice. Okay, so that you can start something in practice. What Anil told, that you will face the problem because you have not designed controller and you have not given the control system a block here. Here you just see what I told you. Here there should be here there should be. If you just see my hand, this arrow, this, it is visible. The cursor
Yes,
is visible.
Yes, sir. Yes, sir.
Here as well as here. Here you have to put in a block which will be the voltage controller, and here there will be block which will give current controller. And in this case there will be only one block. It will be a voltage controller. Okay. And this voltage controller, what I tell my students in usual control class, these are actually the real controllers. Okay. Normal power electronics controller, those who are not bothered about control, they are usually making like this, and they are facing some problem, as I told you. But if you know control, then you will not do this wrong thing. At the beginning itself, you will take care in simulation, and you will put all this control block, and you will design and you will simulate. At least you can start simulation. All of you, that you see without controller block and with controller block, how this simple control system, that converter system run. You will not get the output. You will not get the output at very fast instant. There will be error. There will be very slow response. Even you cannot achieve, output will be lot of fluctuation. Okay, it will may not be stable. So all these problems you will face. But as I told you, to design all this controller, you first know the modeling of this converter. And for this is another important part of my lecture, that is modeling of DC-DC switch mode converter. Since I have considered here DC-DC converter, but that does not mean that this modeling idea is not applicable to inverter. It is also equally applicable to inverter. All these basic things are remain same, only change in equation and you have to see the model. So what are the steps? I will go quickly. As I told you, switching converters are nonlinear time varying system. And here there are many techniques. Even in linear mode technique, there are other techniques also, but here only state space averaging technique, which is an approximation technique, and that approximate that switching converter to linear time invariant system, linear time varying time invariant system. Okay. So for that, some assumptions that filter corner frequency should be much less than the switching frequency, and neglecting, of course, the high frequency component of the converter quantities, and to firmly focus the dominant part of the dynamics of the converter. There are 4 steps while going through this modeling part. First step is you have to formulate, you have to write all the state phase equations of your converter, on state, off state, okay, and you have to write the state space equation, output equation, as well as a state space equation as well as output equations in very standard form, like x dot equal to ax plus bu, y equal to cx plus du. Some cases d is you can neglect, and it is sufficient if you just take y equal to cx. And then step 2, averaging the state variable description using duty cycle. So because you have to approximate it, so that can be approximated, as I told you, if you just consider the ripple is less. Again, the concept of that filter cutoff frequency and all this thing will come, and there you can average it, and this is the average, and that is also mathematically valid. In those are periodic in nature, that can be taken average in matrix also, and this is the average state space equation, and usually here it is called duty cycle average because it is only specified only in terms of duty cycle, not in terms of time period. T is not there here, okay, not switching frequency. So step 3, now you have to go through small AC perturbation analysis, because this equation is highly nonlinear. While coming to actual transfer function of any converter, you will find that then you have to take the uh, linearize it. Now for linearization there are again many concepts, but here again small signal AC perturbation analysis is taken care. So for that, you see that for any variable, suppose x, there are 2 parts. One is capital big X plus x small that hat. So these x is, we will take care about the steady state part, steady state component, DC component, and these x small hat will take care about the AC component. Because around operating point there will be fluctuations, and if it operates, if there is no fluctuation, then this capital thing x or VO or D will take care. And if there is any fluctuation, that may be both way, positive as well as negative, but here only positive is considered. Okay. So after putting this in original equation, you can find out this, and then in step 4, that you can separate out that AC part as well as DC part, and take the Laplace of AC component. Okay. And then you can find out that output voltage, here in this case output is VO, means the output is the voltage of your converter, and input is your duty cycle here, because I just want to find out the modeling of this part only. You have to find out modeling of this PWM controller separately. But in this case, I am bothered about the transfer function output to control. So VO by duty cycle, and that can be taken care by using all these 4 steps. Okay, and finally, these equation is very, very important. Why? Because you have to find out what is exactly A1, A2, B1, B2, C1, C2, and this can be find out from these all basic fundamental equations. And after putting through, then you can find out that this transfer function, and that may be clear from this, from that all these examples. So I have not gone through this basic diagram of boost converter. This is the equivalent circuit diagram. Considering the parasitic elements like series inductor value, resistance value of inductor, and ESR, equivalent series resistance of capacitor, and you know that there are 2 mode of operation, either switch on. During switch on, this is the equivalent circuit, and during switch off, this is the equivalent circuit. Okay, so you have to go for mode 1 and mode 2. You have to write all the equations by just using KVL and KCL, and these are all equations. Then you write the vector matrix form for both mode 1 as well as mode 2. Then you take the averaging, duty cycle averaging like this by multiplying with on time, off time, and divided by the total time, right? Divided by the total time, then you will get these equations. Okay, so what I told you, you have to find that actual equation. What I derive, this is important. This is equally valid for all converters, switching converters. All switching converters, because whatever be the converter in operating in switch mode, that has only 2 mode of operation, either switch is on or switch is off, whether it is a DC-DC converter or inverter or AC-to-DC converter or AC-AC converter, matrix converter, whatever it is. So if you know the equivalent circuit, if you know this, and if you can find out this matrix, then you know all the components like A1, A2, B1, B2, C1, C2. Then after putting this, you can find out this modeling. Then you can find out output to control transfer function like this boost converter. And here you see this is the structure of boost converter considering the parasitic elements. Here you just follow what I told you. In the numerator, in the denominator, you see that complex poles are there, 2 poles. That was there normally in buck converter also. But what is special, that is this 0, and that is there in the right up plane. So because of this right up plane 0, the boost converter is very similar to non-minimum phase system, because it is non-minimum phase. And you know the problem here, it is related to control, actual control system, because while designing controller in non-minimum phase system, it is not unstable. You don't confuse with unstable system. Okay, it is non-minimum phase because it will produce much means more delay in the system. Okay, time delay, you know the time delay system. So here again, it will, if it is produces more delay, then bandwidth will be restricted as well as your response will be slower. Okay, so you have to design the controller. Either you have to modify the topology, or you have to design correctly in control system. Another 0 is there. This 0 is due to that RC. RC means that ESR 0. ESR, but this 0 is situated on the left half of S plane. Okay, what will create problem? That 0 on the right half S plane. and that has to be taken care while designing the control system. Okay. So similarly, buck boost converter, I will not repeat this thing. Here again, you will find once again the similar kind of thing like boost converter. Because of the presence, if you see the physical significance, because of the presence of inductor in the primary side, you know the property of inductor, because during one time it stores energy, and you are thinking that during off time it will immediately transfer energy from primary side to secondary side, but it will not be like that because of inertia of inductance. And because of that, initially it will try to oppose the thing, and because of that it will find that there will be, while going through that, I will just show that on simulation, that while going through it will first undershoot with the change of duty cycle. It will not go to the upper direction. It will not go initially for a few time, that it will try to decrease, rather than it will try to increase with the change of duty cycle. Okay, so these all things are written here in the slide. So now design and implementation of type 2 and type 3 controller. As I told you that the problem of PID controller, I will not repeat it. So you can design that type controller. What is type controller? These are all structure of type controller, type 1, type 2. And type 1 is very similar to that PI controller with the similarity. But PI controller, it will not be useful here. So you have to use for this type controller. So type controller structure is like this, only one pole 0, but additionally one pole at origin. So this is very like similar to lead controller added with one pole at origin, means this pole will remove that, will compensate that your steady state part. Okay, that was not there only lead controller. But what is more important is in type 3 controller, there are two lead controller in cascade added with another pole in origin. And that is also very important, that if I just, we have seen in our work, that if we place the two zeros and two poles at the same locations, means two pole at the same location and two zeros at the same location, then you will get the maximum benefit while designing this control part. Okay. Now, the design of control of this type controller, it is very famous, and using K-factor approach, which is developed by these people, this fellow, Dean Venable, in the year of 1983. Okay, this K-factor is defined as the ratio of the square root of pole frequency to square root of zero frequency for type 2 controller, and ratio of double pole frequency to double zero frequency for type 3 controller. And this is a standard boost converter. Okay, and after taking the parameters, this will be the with all numerical values you have to put it. While going through the design, you must find out that output to control in numerical domain. Okay, so after putting all this thing, you will get this type of transfer function. Now, while going through design, you must have some specific, concept of Bode plot and all this thing. Here you just see from the time that magnitude as well as phase plot, the maximum boost 90 degrees is possible if you select this frequency of this controller at the what we call at the geometrical mean of this controller. Okay, this is very similar to the design of lead controller, but there are few things. The maximum phase boost is there, and cutoff frequency, as I told you, that is the geometrical mean. Now, after putting this thing, and from the concept of K factor, you can find out in terms of K factor and maximum phase boost. So what should be the pole zero location? That in terms of is coming FC and phase boost. FC is the cutoff frequency of the controller. Okay, and that you select less than the switching frequency, at least 10 times of the switching frequency here. So this particular converter operates at 10 kilohertz. So crossover frequency at 1 kilohertz and phase maximum boost, that is in your hand, that how much phase boosting is required. So that is there. Then after putting this thing, the position of pole and zero you can find out, and in this way the transfer function you can find out. Now after putting this transfer function, once again I am telling you that in one trial it may not be possible. So there are a lot of trials of selection of gain and placement of the pole and zero, and particularly cutoff frequency. And you see that it should not be at very high one, the gain of the controller, and it should not be very low one also. It should be in between. You have to select, and there should be a trade-off. Okay. Here at the from the this diagram you see, so it is better to operate while selecting that gain is 1000. It is not. It is in between 500 and 1500 for a particular mode of converter and operation. So after all these things, getting this, you will get the final type 2 controller. Similarly, selection of cutoff frequency. So I am not going to in details. So here cutoff frequency, once again, just seeing that 300 very low, 2 kilohertz and 1 kilohertz, minding that keep in mind that your cutoff, your switching frequency was 10 kilohertz. So if it is 1/5 of that, then you may not get the optimum phase margin. Okay, but if it is below that, then also it is much lower than that. So accordingly, you have to select it. Similarly for type 3 controller, so this is the Bode plot, and accordingly here if you from the basic concept, you know that you can obtain much higher phase boosting, and that is required for booster buck boost converter. So for that, you majority time means a type 3 controller will give better performance. So here the K factor is defined other way, the ratio of double pole frequency to double zero frequency. And from the basic concept, you can find out that pole zero location in terms of that cutoff frequency as well as phase boosting. And if you just select the cutoff frequency, crossover frequency as well as the phase boosting, and accordingly you can find out, just like type 2 controller, the pole zero location, and accordingly you can find out type 3. So here again, lot of trials and errors and the simulation that what should be the optimum value of this pole zero location as well as cutoff frequency as well as the gain. And accordingly, after that, one of my student has done this optimization. After getting the parameters, even you can fine tune with some optimizations of computing techniques. And there are some results. Here you find that there are different optimization technique, PSO, GSA, along with K factor, normal K factor, type 2, type 3 controller. And here you find that for this particular operation, the GSA based type 3 controller is showing much better response than other controller. And then implementation. Okay, after getting the design of this thing, this particular operation has done with G-Space controller. So you just see that one voltage sensor is used LV25P, which isolates primary side, secondary side. Even though we have taken care about that conditioning, circuit conditioning part, what we call signal conditioning, by using filter and all these other things, means voltage attenuation, because your output voltage should not be more than 5 volt, and accordingly this is the circuit. You just see the filter part is taken care low pass by this RC component, and this Zener back to back is connected here. Okay, so that your output is not more than that, and accordingly you are designing. This is the actual circuit diagram, and this is the actual picture of hardware setup. and these are all results. And finally, in practice, you have to see whether your controller is working properly or not. That you have to check. How do you check that? By changing the load. And here you just see the by changing load, how the dynamic response performs. Okay. So this is the current response, and these are all voltage response. So these are again comparing with practice with the change up with the K factor normal controller with optimized type 3 controller, and obviously if we compare these two responses, here you see this is much better than this one, both for positive going step as well as negative going steps. Okay, so if you take this one, if it is okay for you, then I will shift to the other parts. Otherwise, I will stop it here.
Yes, sir. Okay, sir.
Sir,
Bolo, time is up.
sir, actually it is already 11:52. So if you take another option, so it will. Okay, now candidates can ask question about the topic and all.
Yeah, that will be better if you just go for that way. Otherwise, I can just only show the slide so that how the things have been modified with the advanced power electronics converter and with the usual this control and modeling. This is for tri-state converter, and normal modeling is done. Here you just see there is no right up plane 0. This is the response of basic boost converter. Here you see initially it was coming down, then it is going up, but it was not the case of tri-state converter. So these are all steady state responses in practice as well as in simulation. These are all responses in real time with the change of load both in positive step as well as negative step. So other converter like tri-state buck boost converter, these are the responses. Okay. So you have to show all these things. Interleave converter. Interleave means paralleling of converters. Here I will just see that how things are interleaved. Two converters connected in parallel. There are other objectives here to reduce the ripple and all these things so that you can see in this waveform that with the change of duty cycle how there is a large difference with ripple with a normal boost converter and interleave converter. Okay, and interleave tri-state buck boost converter or buck boost converter, here both the things are embedded, means you can get the both advantage of tri-stating as well as your interleaving. These are some special type converters anyway, but I can you just have an experience that how things are done in practice. These are all practical results. It will not come in one trial or single day. You have to do practice. And you have to go for all the analysis like ripple efficiency. Then some converters like these converters, boost converter, buck boost converters, particularly some applications like solar fuel cell applications, battery charging. There you have to take the output from fuel cell or solar cell. Okay, but that output is not that high. So if you put simple boost converter or buck boost converter, then gain is limited. So particularly for that concept, you have to go for that higher gain converter. There are different topologies in the literature. We have also developed in our laboratory some more converters, but after developing this topology, you have to test it within closed loop. Again, once again, you have to go through all modes, okay, and then go for the modeling, then closed loop control, and finally you have to show that the response of current. Here you see the inductor current, there is a ripple, but this current or ripple is expected, but in voltage you just see if there is a sudden increase of load, initially there is a voltage high rise, but after that it will maintain that your steady state nominal voltage. Similarly, for current as well as your wave. These are all steady state waveform. An analysis of that with duty cycle, with efficiency, and your ripple, okay, load voltage ripple. Similarly, another converter like input parallel output series buck boost converter. So all these converter are analyzed. That is important. You have to go through correctly modeling, then design of controller. All right, and then you have to run, because here you can do all these things in any form, either analog. But for the timing, I have shown with the analog control. But we have also developed all controller in this space, as well as some people are also working here in FPGA along with microcontroller also. So there are many things. Many things means working with the controller, working with the converter and control. It is not only the concept of design of converter or design of concept of control. You need sophisticated hand of power electronics. You need the idea of PCB. You need the design of converter control, and ultimately you have to run. And the funny thing is that after designing so many things, you are not sure that your converter will run in closed loop. And that is the most challenging task. While designing after closed loop control, you will find, okay, those who are research scholars, those who are tech students, they may be frustrated after having long time that explain that, that my circuit is not working. Okay, but I am giving you assurance that if you know the basic idea, step by step, one step to other step, every step is important. Because suppose if you design one converter and you are thinking that it will give from 5 volt to 100 volt in one step, even if you can go for in one step, then what should be the design of transformer? That is also equally important. Means design of magnetics. And once again, design of magnetics means again design of machine, transformer, and particularly hands-on experience of designing coil, right? Because ready-made transformer you can't purchase. Means you can purchase, but that will not be sufficient for you, because you need some other form of means design, some other form of flux density, turns ratio, polarity. So everything you have to taken care. Okay, I think I should stop here because I have a lot of slides. But anyway, I should stop here because you have some other session. So if you have any question, you can ask. Otherwise, you may take my phone number or email ID from the coordinator, Dr. Minal Kumar, for your applications or your practical idea. Anytime you can ask, or anytime you can give a mail so that I can respond accordingly. Thank you.
Yes, any questions from the participants? Okay, sir. They will share your email ID and contact if any issue, if any queries are there, they may contact you, sir. So we'll end up the session with a small vote of thanks. Sir, thank you, sir, for an informative presentation. You have touched several practical aspects related to the design of power control in detail. Sir, you talked about direct ratio control, voltage feedback control, current mode control, voltage mode control, and the problem with right half pole zero in boost and buck boost converters. And you talked about the type 1, type 2, type 3 controllers, and many more things which you need to explain, but due to the limited time, we couldn't hear you much in detail the other part of it. Thank you, sir, so much for spending your valuable time and sharing so much of information with us. Thank you, sir.
Thank you. Welcome. Okay.
Thank you.
So
Okay, sir.
May I leave now?
Yes, sir. Yes, sir. All the participants will meet again at 12:45. Prior to that, only 5 minutes earlier to that. So for the next session, thank you. Good afternoon, sir.
Hello, good afternoon, everyone. Yeah.
Sir, can we start our session, sir?
Yeah, sure. Sure, we can.
So let me just give a summary of your previous session, sir, because you already have taken one session earlier.
Yeah, sure.
Good afternoon, sir. I once again welcome you to the FDP program on recent trends of control systems and power item converters. Sir, in your early session, you have covered several points related to issues in grid interface PV systems, trends in PV converter systems, MPPT techniques and control, gave a clear understanding of single stage and two stage converter topologies. And it was a very interesting and interactive session with a lot of queries from the participants. Now, once again, we are eagerly awaiting to listen from you on the topic that you are going to present today. And with this small summary of your earlier session, I would like to hand over the session for further proceedings.
Yeah, thank you. Thank you for the for summary of last session. And yeah, we have discussed a lot of things related to system which is directly connected with the grid. I mean, if you have any power converter, and through power converter we want to interface our renewable energy sources to the grid. So what would be the control and how we can go to control of these power electronics. So in this case, related to control of power electronics, we have handled only one PI controller. Here we have handled only one PI controller, as if you people had seen my lecture. So in that particular lecture, we have one current control, and in that particular current control, one PI controller is implemented that controls the voltage, DC link voltage, and which is the major requirement of a grid connected converter, grid connected PV system, grid connected wind energy conversion system. I think my professor yesterday has discussed a lot of things related to wind energy and how we can go for the control of its integration with the grid. So further moving ahead with this lecture, here what we will do, this is the extension of those who are working in this area. They will know that how we can integrate, apart from suppose we have PV array and battery energy storage, so how we can develop these systems for rural areas. The system which we have discussed till now in last lecture, we have discussed the lecture or discussed the topology which is much familiar for the urban area, where the electricity supply is very rugged, or what we can say very reliable. It is not, I mean, disappearing for a particular time. But if we are in India and we supposed to develop system which is very feasible for Indian grid scenario. So if we go to the rural areas, in rural areas, what we are observing, there is continuously fluctuation in the grid. So it has forced me as well as the researcher in India that they have to develop a system instead of, okay, that grid connected system is means the weight of the grid connected system and its control is very less, as well as because the battery bank is not there. But what is your requirement basically? I mean, you are going for a grid connected system or the system which is going to be feasible for rural area also. Because in rural areas, there is continuously fluctuation. As I told you, there is continuously fluctuation of grid supply. So if there is continuously fluctuation, or out of 24 hours, there is 3 to 4 hour fluctuation in the supply, or there is outage of, we can say there is grid outage for 3 to 4 hours. So you cannot utilize your grid interactive PV system for 3 to 4 hours. So payback period of power converter, payback period of PV system will be reduced. So initially, during my PhD, I'm telling you again one story that during my PhD, I have worked. This screen is visible first page of this my PPT is visible to
Yeah.
everyone?
Yes, sir. Yes.
Okay, thank you. So during my PhD, those who are a scholar, they can understand, and that is the very difficult thing, which area we have to select. With the help of your guide, you can select the area, but sometimes you realize that lots of things has been done in this particular area. Like if we talk about simple grid connected PV system, power converter, or grid connected power converter, grid connected PV systems, IIT Bombay has started publishing on this particular topic from, I think, 2007 onward. Before that, few literatures, Albag University, they have published, and then few publication came from the USA. Okay, so, but after 2007, IIT Bombay and IIC Bangalore, they have started publishing on this grid connected PV system. And in IIT Delhi, we have started on PV system. Earlier we were working, but on full-fledged, we started, I think 2012 and 13, when we got the solar simulator as well as this 10 kilowatt installation at the rooftop of PV at the means above the laboratory. So we started in 2012 and 13. So many of my colleague, my senior, they have worked on this particular topic, the grid connected PV system. Initially, they were working on power quality conditioner. Then they have interfaced this renewable energy, and they have funded out what are the issue and how we can integrate these PV power to the grid. But and I joined my PhD in 2015. Okay, so after that, what happened? Initially, my professor has put me in this particular topic. They have allotted me this topic, so I started working on this. I have published around 8 to 10 transaction as well as IET papers, IET and means the journal papers. Initially, a period of, I was also the part of MTech, so of IIT Delhi. So during initially 3 to 4 years, I have published these papers. But after that, what happened? After 2 years of my PhD, I got one comment from the reviewer that this is the topology which is going to be, already reported by the literatures. What is your contribution? Because till that time I have reported many controls, many issues related to grid connected system. So apart from system, apart from control, what is your new contribution in the topology? Topology means simple grid connected system we are having. Grid connected system, we have solar PV array. We are talking about two-stage system, so boost converter is there, and then VSC we are having for DC to AC conversion. So they have rejected that paper. So I went to my professor and I said this is the comment, and we got from the one of the reviewer, and they are not appreciating this work. So how we have to proceed? So it has taken to think. Uh, for thinking, do the literature review, it is easy. But when the part will come for the implementation, when you want to you have developed a system, you have do the literature review, you have find it out the objective, what is the research scope, what are the comparison between your system and whatever the literatures who means researcher who have already reported. After that, you have to go for the simulation. You have to simulate that particular topology. Is it feasible or not? Then you have to move for the experimental verification and all those things. So this is the process for research. Those who are the students, MTech student, PhD student, they can understand these things. First, we have to go to the literature review. Then we have to follow the procedure. So same way, what I did after 2 years of my PhD, I was very frustrated when I got this comment. Then what I did, I have gone through my professor, and he suggested find out some literatures what the trend now after the grid connected. So what I find it out that time that after 6 to 7 months, means people are doing literature review initially, I mean 6 to 7 months when they joined the PhD. But after 2 year and 2 year plus 2 year, 4 year of my MTech and PhD, I have started my literature review on these PV systems who can also feasible for rural areas. I mean, who can operate in grid connected mode, but whenever the utility disappears, whenever grid outage condition is happening in the system, what would be the scenario? How you will maintain the synchronization during the appearance of grid, and how you will island your system, how you will disconnect your system from the utility grid. So after 6 to 7 months doing the literature review and finding out the clear contribution, what are those means everyone is writing the research paper, everyone doing the research, but what is your clear contribution? If you are doing the literature review, you can see after the introduction there are 5 to 6 points people used to do the contribution. Okay, so if you are able to clearly mention that these are my contribution in this particular paper, then reviewer will realize, yes, they have cited the paper as well as they have cited the contribution. What is the main contribution as compared to other literatures, whatever they have reported. So after that, we have proposed this particular topology, and further we got, next 10 to 15 transaction as well as IET paper I got in this particular paper. What was the contribution toward the control side, as well as topology is also modified in terms of grid connection, islanding, then how we can synchronize this particular system with the utility grid, how we can disconnect. Okay, so along with multi-mode features, we are not iterating the power quality, number one, which we have already reported, means power quality issues will be there, but how we can make this system which is more feasible for rural areas, for villages, how we can operate using multi-mode functionality. So you need to understand, if you are operating a PV system in standalone mode. Standalone, I think everyone is able to understand what is standalone. Means grid is not there. So if this system is operating in standalone, but daytime you have insolation, nighttime you don't have. So one topology I have reported that is based on without battery, which is operated in grid connected as well as in standalone mode. And that is successfully, I have published this IEEE transaction industrial application recently. So they have appreciated now and they have accepted that this, yes, there is some contribution in this particular research. So here, moving ahead, here we want to develop some topology which can be feasible for rural areas, but we have to put the battery along with it. Otherwise, night time when grid disappears, at that particular moment, we cannot utilize this particular system for standalone mode. So that is the main issue. Yes, thank you. हाँ सर, मुझे 2 बच जाएंगे आपसे, बताइए। 1 मिनट। One So here we are developing a system which is having multi-mode features, and you have to believe that this is the, what we can say, whole autonomous system. We need not to, control or switch anything. We need not to switch on or switch off. Once you will switch on, everything, whatever, where the battery power will go, or we need to charge the battery, we need to discharge the battery, or we need to feed the power to the battery, this control action will take care of all those things. So here, if we see the motivation and objective for this particular research, so recently MNRE has taken several steps. Why? Because when grid outage happened in last few years or before 2015, we have realized that if people are using diesel generators or diesel engine for during the outage of utility grid, they were using a diesel engine to supply power to power the house or to power the hospitals, data centers, all those things. But due to the hike of diesel fuel sources and the other thing you can realize in cities like Delhi, there is, air pollution, which is very dangerous for humankind. So therefore, we have to avoid this diesel engine due to hike in price as well as for atmospheric conditions. And energy storage is required to avoid these outage of electricity. If outage of electricity is happening, so we have to avoid these this outage. So we have the solution. We have to include this energy storage with our system. The PV system with battery and grid synchronization, desynchronization may be a good solution for residential area. Okay, you can put a small battery along with the PV array. Suppose you have installed a small PV array along with your battery, and there is grid outage. So we need not to stop the system. In grid connected PV system, what we have realized, what was the demerit? We have to shut down. We don't have option because from the PV array side that is operating in MPPT, and if it is operating in MPPT, somebody who's working in the line and clearing the fault, he may get the shock. So we need to shut down our system. Once the fault is clear, then we can connect our system with the grid. However, in this case, the same system will be operated in islanded mode. And we have some reliable switches, we have some reliable control by sensing some parameters, and these synchronization and desynchronization will take place according to these parameters. These parameters we have to include in our control. And there is a standard which is known as IEEE 1547. So if grid parameters are within the limit, then the system will be synchronized with the grid. If these parameters are not in the limit, then the system will be desynchronized with the utility, and we can operate your system in a standalone mode. However, what are the issue with the solar inverter, grid tied solar inverter? From the protection issue, these solar inverter are mandatory shutdown under loss of utility grid. However, this multi-mode features based system is developed to establish the mini grid to supply power to the consumer load. I would say continuous power supply to the consumer loads. Okay, continuous power. Consumer will not experience any outage of electricity. Suppose we have data center and we have these hospital, and some doctor is doing operation, and you can think if electricity is not there, sudden there is outage of electricity. So what will happen? Patient will die. However, in this case, whenever there is, even though you will not realize there is outage, when grid outage is there, immediately battery will take place and battery will supply. Or in daytime, if PV is available, PV will send the power to the consumer loads. Okay, we need not to shut down anything. In photovoltaic battery energy storage microgrid system, extracted active power is shared between the load and utility. So we have this PV battery system, and if SOC of the battery is within the limit, like there is certain standard, lower limit should not go below 20% and higher limit should not go above 80%. So if SOC of the battery is more than 80% and load demand is less than the generation from the PV, whatever the generated power from the PV, if load is less, so rest of the power we can share with the utility grid during the grid connected mode. Moreover, this microgrid can be operated under outage of PV source and utility grid. Under outage of utility grid as well as outage of PV source. Suppose night time, both the sources are not there. PV already not there and suddenly grid outage is there. So what will happen? Battery system will continuously in the standalone mode and battery will supply power to the loads. However, in case of grid tied solar inverter, utility is not there, then we have to shut down our system, which is turn increase the utilization factor, or once the system is shut down, so payback period of power converter will be reduced. However, which increase the utilization factor of this power converter, which is used for PVBSS system, and it decreases the payback period of power. Benefit of proposed microgrid: reduction in distribution losses. That is the same. We have bidirectional power flow capability. We can import or export power from the grid. No need of bulky magnetic transformers. So what we used to see in case of uninterrupted power supply, everyone has these UPS at our home. So generally what we use single phase this battery bank, battery of 6 or 12 volt, and we are stepping up the voltage of the battery so that we can, because your fan or some instrument which are at home, they are working at 230 volt, and to get the 230 volt at the output of converter, you must have 400 volt source DC bus, 400 volt DC bus at the input of the converter. So 12 volt using magnetic transformer or DC, we have seen this bulky magnetic transformer to boost the voltage to meet the DC bus requirement. The another feature, using static switches, this is very important point for this system. Using static switches, the reliability of the system is improved. How the reliability is improved? I mean, these static switches are nothing but these are the power electronic switches. These are the power electronic switches which are used to connect and disconnect the utility grid. Which are used to connect and disconnect with the utility grid. So if you are having any kind of interruption toward the utility grid, these static switches will be activated. Activated means they will get the signal from the synchronization and islanding control. Because we are sensing some utility parameter, we are giving the signal to these switches in terms of 1 or 0 or 0. Okay, so when we will give 1, so these switches will be activated. I mean, they will be on. When they will get the 0, means in this fashion we are giving the signal 1, then 0, 1, 0. So these are nothing but pulses. Okay, so when they are in on state, they will get 1. When they are off, they will get 0 signal. Means here we will get 0 and here. So in on state, if the criteria of IEEE 1547 is meeting, means 1547. So this is the standard, I would say, IEEE standard, and this standard, if you it is available in the Google also, you can search this just IEEE 1547. So all the conditions are given in this standard. when we are going to connect our power converter with the utility grid. When we are going to connect our power converter with the utility grid. So if the output voltage of power converter as well as the utility voltage, so there are three parameters: voltage, frequency, and phase. So phase angle, the difference between power converter output and power converter output voltage angle as well as grid voltage angle must be less than 3 degree. Okay, so let me share the whiteboard so that you can understand that how we are comparing these frequency and voltage. So here, what I'm talking about, we are having one power converter which we have earlier, I have shown you. Here we have DC bus and here we have power converter, and we have some inductance here. And at the point of common coupling, we have connected some switches. Okay, some we can say some switches here. I will show you the exact IGBT switch we have connected. So these are the static switches. These are nothing but static transfer switches, and then we have our utility grid here. So what we have to say when we are going for experimental verification. So what we have to see, we have to sense the parameter at this point. We have to sense the parameter at this particular point. Voltage and current at this particular point, voltage and current at this particular point. So to develop the synchronization and islanding control, what we will see these parameters. Okay, we have to see the magnitude of VG. Suppose there is interruption, there is some line to line fault, line to ground fault, or LLG fault, line to ground fault. Okay, so these faults are occurring, and once these fault will be cleared, then only we can get the actual voltage. So IEEE 547. 1547. What it says, the magnitude of VG, it should have 0.88 to 1.1 per unit. The value of this VG must be in between 0.88 to 1.1 per unit. Then only these switches will be on. If the frequency variation is plus minus 0.2 Hz, not more than that. And there is, so here you have sensed the voltage, and so suppose this is the load voltage, here load is also connected, so at this point we are considering that VL, and we have this VG. So correspondingly we will be having some theta L and we are having some theta G. Okay, the difference between theta G and theta L must be less than 3 degree. The difference between theta G and theta L must be less than 3 degree. If you are satisfying these three conditions, then only you are able to, or your switches will be on, or electricity supplier will say that, are you following these standards? These are the few standards related to harmonic. We have harmonic standard, which I have earlier told you, IEEE 519. Okay, TSD of voltage and current must be less than 5%. Okay, TSD of voltage and current must be less than 5%. So if you are following these standards, you are eligible to connect your microgrid your PV system, your wind energy conversion system with the utility grid. Otherwise, if these magnitude is your converter output is varying, I have told you one example of this when the inverter trips. One story I told you when the inverter get trips, when it start drawing a reactive power because voltage is not balanced. So you have to keep the voltage balance, you have to keep the frequency balance, you have to keep the angle balance also. So magnitude, directly you can measure, you will get the magnitude. But the question is how you will get the frequency and phase. How you will get the frequency and phase. For that purpose, people are using PLL. You might have a very famous name or very famous unit, very famous control, PLL, phase log loop. To derive, so you will supply the sensed value and you will apply the PLL block, it will give the frequency and phase. So suppose VG you have given, so you will give the information of FG and theta G. If you will give theta VL, so it will give you the FL as well as theta. Okay. If you get these limits or if you are following these limits, then only you can connect your system with the utility. So these are the few scenarios, few conditions which you have to follow with this particular thing. So again, I'm moving to PPT. So this way we can use these static transfer switches so that the reliability of the system is improved. Reliability means when we are operating this system in grid connected mode, when we are operating this system in standalone mode. In both the modes, we will not affect or we will not interrupt the supply across the consumer loads. So reliability of the system automatically improves. Performance verification under point of common coupling variation. So we have seen in last lecture also, and in this lecture we can vary this PCC within the limit of that voltage. If voltage variation is going beyond that particular limit, our system will not work. So there will be chattering issue, there will be some other various issues, harmonic issue related to that. So we have to follow that particular standard. Indirect cost reduction, as well as we have seen in last lecture also, use of PV feed forward term. So how we can connect these PV feed forward, how we will include in our control. So we have seen. Now classification, so based on again the number of phases, single phase, three phase, and again single stage, two stage, but after single stage and two stage, it can be batteryless. This can be a batteryless. How batteryless? It can operate in standalone as well as in grid connected. But how earlier we have seen that system is able to operate only in grid connected mode. Battery based will be in battery with bidirectional converter. However, in case of two stage, batteryless, battery based, and battery based can be battery without control, battery with bidirectional converter control. Now, my question to the participants, audience, whatever you say, can this single stage system, is having, why it is not having battery without control? I mean, can we control battery without control? Means we don't have any kind of software control. We can see it manually. I mean, now it is charged 80% and we can switch off. So why we cannot connect battery without control with the single stage system? My question is, again, I'm going to repeat it. Why we cannot connect battery without control? Here we have categorized again single stage and two stage and type of battery connections. how we can connect these batteries with our systems. So my question, why we are not able to connecting battery without control with the single stage system? I think very easy question or very easy concept to think. Anyone can answer? Why we are not going for this type of connection? So here, what you will observe in case of single stage, this, as I told you, PV array is directly coupled with the converter, DC to AC converter, and then if you are having battery, so battery connection would be like that. I mean, let me. So we have PV array here, and then we have DC to AC inverter, and then battery is connected here. Okay, battery is connected here. Battery bank, you have two battery banks here. So in this particular thing, what will happen? And in case of two stages, we have boost converter, and then we have here bidirectional converter also. However, if we see that in single stage, we don't have any decoupling unit here. So current will follow the shortest path, and whatever the rating of PV array you have designed, suppose I have designed a rating of 5 kilowatt, whole power will dump to the battery. Whole power will dump to the battery. And if you're, suppose you have applied a battery of 2 kilowatt and the battery rating is less than, so it may blast. If you are dumping more than 80% or 90% SOC, so battery may blast. Because here there is no decoupling term. You cannot control this because here without battery is also not control. Here we don't have any control as such as boost converter or some other. So in case of single stage, we cannot connect this battery directly with the PV array without control. We should have bidirectional converter here. We must have, I would say. We cannot connect our battery directly to the PV array as there is no control unit. And in this case, two stages, we have boost converter here. So through MPPT, we can control the duty ratio of PV array. That now I want to charge a battery of these 2 kilowatt battery with a current rating of 1 ampere. So what I will do, I will operate this PV array in off MPP mode. I will operate this PV array in off MPP mode. So what would be the benefit by operating off MPP mode? Whatever the power demand, it is came from the battery, that amount of power I will fed to the battery. Suppose now I have to reduce the current, so I will operate this PV array in off MPP mode. Off MPP mode is nothing but, I mean, suppose I'm operating here, now I will reduce the power here. Okay, I will reduce the power. So earlier I was operating here at peak power, now I will operate here. So less power, less current will dump to the battery. Less current now will dump to the battery. When battery SOC is increasing, PV array power will decrease. Okay? If we want to charge the battery only. If we have sufficient storage, I mean, suppose we have another battery or we have grid here. So grid is an infinite storage element. So we can rest of the power, whatever the power is required to the battery, we can inject to the battery and rest of the power can be fed to the grid. So always we will operate in MPP mode. But it is not possible in case of single stage system because current will follow shortest path. So battery will act as a load for this PV system. Battery will act as a load for this particular PV system. Similarly, the three-phase system is also categorized. Three-phase, three-wire, again two stage, and but here the type of connections of battery are different. how we are going for a connection of we are going a topology for batteryless, or we are going a topology for battery based. Okay, so it will depend on the type of battery connections. So conventional two-stage PV system we have seen. What was the problem in this system? The utilization factor was poor. I mean, utilization factor means daytime PV array is available, but nighttime we cannot utilize. So this converter we need to shut down. So nighttime we cannot utilize this converter. Okay, so it is not utilized more than 2/3 of the day. What we did after that, we have realized we can apply load, we can modify the control. So daytime it is working as a PV system, okay, and nighttime it is working as a power quality conditioner. So nighttime it will draw the power like this, and daytime if PV array is sufficient, then the power flow will be like this. Okay, so daytime this load which is connected for the compensation, it will draw power from the grid. Daytime it will draw power from the PV array, and nighttime it will draw power from the utility grid. And nighttime this only harmonic compensation will be there. Daytime it will have harmonic compensation as well as active power, which is taken from the PV array, or which is injected from the PV array. But what is the issue with this system? Suppose if grid fails, if grid fails, again the utilization factor of this power converter will be poor. Why? Because you don't have any kind of voltage control, you don't have any kind of standalone control there. So grid gone, your control will not work, so you need to shut down. Otherwise, what will happen? Here, either you will damage the DC bus, because here the power continues, because the power flow will not be completed. If the power flow is not there, here you have cut off the system, so this DC bus will start increasing, and it will go beyond your blocking capacity of this particular switch. I told you what is the blocking capacity of these switches. We have certain safety margin. DC bus voltage plus safety margin will decide the rating of this converter. And if this voltage, if you are increasing continuous power from the PV array, this voltage may go beyond 900 or 1200 volt, which may damage your IGBT. So you may damage our converter and the system will be damaged and it will not. So what could be the solution for this particular system? Solution is, can we operate this system in standalone as well as grid connected mode? So we, after 9 to 10 months, we came across this system without battery. Remember, without battery. Here there is no battery connections. Here there is no battery connections. So what happened in this system? We have taken a PV array simple, and simply for verification purpose we have taken single stage. There is no boost converter, and this converter 2-leg VSC, now it is controlled in current control. This is combined improved proportional NLMS soft computing based control, and other side we have taken one islanded control. So this is the current control and this is the voltage control. Voltage control means not DC bus voltage control. Not DC bus voltage control. So what does it mean? Control at the voltage control at these points. I mean, we in islanded mode, we have to generate the frequency reference and the sinusoidal voltage. Our responsibility is to generate a 50 hertz sinusoidal voltage so that we can feed the power to the loads. Otherwise, load will not take the power, because these load, this is the single phase system. So these load are rated 230 volt and 50 hertz supply. So they require 230 volt and 50 hertz. If you are not able to generate 230 volt and 50 hertz from your converter output, this load either it will damage or they will not take the supply, or it will be ripped. So what we did, we have control this frequency, phase as well as magnitude of voltage using islanded control. And these signal grid recovery and grid failure, they are coming from the synchronization and islanded control. I will show you these control, how these control, we are proceeding with these controls. And after that, this is the point of common coupling where utility grid, where nonlinear load, converter output and RC filter are connected. And see the STS. This is very important part for this particular system which we have developed. So we have connected back-to-back switches in this condition. Why back-to-back switches? Why we are not connecting only one switch? We can also go with the one switch if it is a bidirectional switch, if it is controlled in for both the power, either power drawn from the grid or power is supplied to the grid. So the power, if power is supplied to the grid, so here the power flow will be like that. So what will happen? This switch will get 1. How the power flow will take place, now I'm going to tell you. Because we need to also take care of losses as electrical engineer. As electrical engineer, we have to take care of losses also. So we cannot switch on both the switches at a one time because there is significant switching losses in the IGBTs. So what we will do, when the power flow from the converter to the grid, so we will switch on this switch which is close to PCC. And the second switch, diode will be switched on. Only diode will be switched on, so that we will be having power flow from, because this diode will be in forward bias for the power which is coming from PCC to the grid. Okay, so the power flow will be like that. In second case, what we will do, we'll be having, suppose PV array is not in the function or the enough power is not there. So load will draw the power from the utility grid, power flow from the utility grid to the nonlinear load. So at that, the switch which is close to utility grid will be on, and diode of second switch to complete the path means it will be in forward bias. This diode will be in forward bias. So this way we will get the bidirectional power flow which I have introduced in the introduction. We will get the bidirectional power flow from utility grid to the load or from solar to the grid. Okay. And you won't remember, I mean, see here, we have published this particular paper in ATAL transaction on industry application without battery, which is having finite state machine based islanding and synchronization under grid outage. Recently it is published in December. So this topology we have invented at that time, and we have published many papers in these particular thing. So if here we are not connecting any battery along with this system, but again, so I have told you the disadvantage of each topology. This is not having nighttime, we cannot operate. This is the topology. If grid is not there, we cannot operate. Again, this is the topology. If grid is not there, we can operate. But what about the nighttime? Nighttime, suppose grid as well as PV array is not there. So we don't have any kind of other source to supply the power. So we have some backup. So again, this topology is also having some demerit, like if both the sources, utility grid and PV array is not there, then we cannot operate. If utility grid is not there, PV array is there, we can operate this system. But if both the sources are not there, then we are helpless. I mean, we cannot operate this particular system. So what we did, we have proposed another topology, PV array, grid, and we have connected one battery at the DC bus using bidirectional converter. With the bidirectional converter. So in this particular topology, what we did, this only the thing which we have changed the control, because battery we have to keep in picture. Battery control we have to include. So battery control we have included, as well as what we did, we have also gone through this bidirectional converter. And this bidirectional converter is nothing but, this is the buck boost converter. Buck boost converter. So when boosting is taking place, so in case of boosting, we have to support the DC bus. So the power flow from the battery to the DC bus. In buck mode, what we have to charge this particular battery. The power flow from the DC bus to the battery. So this way we can connect our battery to the DC bus. So this is the method how we are proceeding with the topology, or how we are changing the topology step by step. I mean, starting from solar inverter, we have reached to a microgrid. A microgrid, a small microgrid, I would not say a very large microgrid which is operating in 100 kilowatt or megawatt range, but this is the residential microgrid for a particular home. Suppose we have 5 kilowatt, we have a 5 kilowatt PV array and 3 to 4 kilowatt hour battery, and then we have a small single phase grid. Then we can install this system, which will be very efficient, as well as which will be very effective for these particular operational areas. We have designed the boost inductor, which is around 5 millihenry. Then buck boost inductor we have designed, which is also we have chosen 5 millihenry. And switching frequency here, you can see that we have taken as 10 kilohertz. 10 kilohertz switching frequency we are switching, because we are using IGBT. If you are able to use some advanced devices like SiC or some GaN based devices, gallium nitride based devices, then you can go for higher switching frequency, you can go for loss reduction and all those things. And we have designed the DC bus capacitor, which is chosen as 2400 microfarad. Then RC filter inductance, or we can say coupling inductor, which is chosen as 4 millihenry. The calculated value was 3.6. And we have DC bus voltage selection. For single phase system we have taken 400. For three phase we have also taken, due to some restriction in the laboratory, we have also taken three phase DC bus voltage for three phase system 400, and then 230 volt grid we have taken three phase grid also. Single phase here we have taken 400. For three phase we have also taken 400. And then very discharging element for battery. So you can see the value of these internal parameter of the battery. You can see the value of capacitance, that is very large, 52,000 farad. Why such large value? Because we need to sustain Coulomb for a longer period. Okay, we don't want our battery should discharge in very short period. And again the control. So this control you have already seen. What is the difference? This battery we have connected, so we should have a control over the battery. So for this purpose we have taken same concept we have applied, whatever we have selected for PV feed forward. Okay, VPV, IPV we have taken, then we have derived some PV feed forward. And from toward the battery contribution, we have taken a battery parameter, PV battery, and with the information of grid voltage, we have derived one battery parameter. In grid connected mode, we want to discharge the battery, because sometimes if we want to support the grid, I mean during the larger load demand, evening time or night time, when there is load demand which is very larger. So at that particular moment, we can also discharge the battery so that we can support the grid. We can reduce the burden on the utility grid if you have a spare capacity of the battery. And then we are having this we can also estimate the active component. Active component again multiplied with the unit template. Unit template I already told you how we will estimate, and we have estimated the reference grid current, and reference grid current is compared with the sensed grid current to generate the grid connected. And remember, this current control or this grid connected mode only will be activated when these STS will get one signal. These STS will get one signal. So this control will take care like that. If these utility parameters or the converter output parameter are not in the range which I have already decided, so this action, this STS will be 0. This STS will be 0. In that condition, this control will be activated. So in current control mode, we have very well-established frequency, well-established theta, well-established all those things. However, in case of current control mode, in case of voltage control mode, we have to generate this voltage. We have sensed voltage at the point of common coupling, but this VL reference we have to generate. So what would be the VL reference? That is nothing but Vm sin omega t for single phase system. And this omega is very important. This phase in frequency is very important, which we have to generate. So VL reference will compare with the actual VL, that is the load voltage, and it will given to the PI controller. And this PI controller will regulate this load voltages, will get the reference VSC current, load current, whatever you can say, because in standalone mode, the output converter output current will be same as the load current. So sensed load current, we will compare with the actual VSC current to supply the pulses to this particular system. So this way, this voltage control mode, because at the point of common coupling, we have to regulate the voltage in case of standalone mode. So this thing will be, and these are the few equations, governing equation for this particular current control mode. How we will calculate the VT, how you will calculate the unit template, unit vectors, unit template, whatever. This is the equation for soft computing control. This is the PV feed forward term, which we have estimated with the help of VT and PV array power. Then net active, both the battery parameter and PV parameter will be subtracted so that we can inject the net power to the utility grid, and then reference current and then error which is given. Now this is very important. Cascaded PI control for battery control. How you will control the battery? Because we have bidirectional converter, and this bidirectional converter in terms of voltage and current, it will give the information that how much SOC. We have various algorithm, we have various SOC meters to estimate the SOC, that now the SOC of the battery is 80%, and according voltage and current, these are the SOCs according to the battery voltage and battery current. So we will estimate these parameters. So we will take VDC here, VDC reference. Then now you can see that the DC link control is shifted to the bidirectional converter. Earlier, in case of grid tied mode, we don't have bidirectional converter, so DC bus voltage control was in the VSC control. Now this DC bus voltage, because according to DC bus, we will decide the operation of battery. That suppose you have, let's suppose you have taken a 400 volt. If this voltage is going above the reference value, suppose it is going 404, and suppose once it is going 404 and once it is coming 395. So in case of 395, we have to support the DC bus. We have to bring this 395 to 400. 395, if voltage drops to 395, so there are two conditions. Either there is regulation in the PI controller, either the problem in the regulation in the PI controller, or if your PI controller is well tuned, there is more demand of power, or power is reduced at the DC bus. It will realize that there is reduction in the power. Earlier, suppose PV source is enough, but suddenly PV source gone to the zero. So DC bus voltage will reduce. At that particular moment, your battery should support this particular DC bus so that this DC bus voltage can be boosted to the 400. And for this particular condition, the battery will operate in boost mode. Battery will supply power to the DC bus. And this reference, this actual voltage is there, we will reference. And whenever, suppose we have outage of distribution and PV array demand is more than the load. Suppose, load demand is less than the PV array generation. So 5 kilowatt if you are generating, 2 kilowatt load is there, rest 3 kilowatt will dump at the DC bus. If your battery can take 3 kilowatt, suppose it is at 20% SOC, you can dump 3 kilowatt, but if it's not taking, you have to operate your system in off MPP. So the battery will decide that how much power, how we have to control this DC link voltage. Means, and during the autonomous operation, PV array gone, so battery has to support. If battery don't have enough charge, so the grid will also charge the battery. The DC link will be supported from the utility grid also, because one term you have included in the DC bus. Sorry, in the grid connected mode. Battery term you have included in the grid connected mode. Let me go to the directly that link. So this battery will support the grid, or we can take the power from the utility grid. In this control we can see we have plus, we can also subtract, we can take plus and minus here as per the requirement of the battery. We need to charge the battery in grid connected mode, or we need to discharge the battery. And this is the bidirectional control when we want to support the DC bus. Okay, so battery, when it will operate in the boost mode, the battery to the DC link and supply power to the dedicated, thus discharges the battery. When the PV power is available and grid outage is there, then the DC bus voltage rises. Suppose there is certain outage of grid and PV power is more than the load demand. So the DC bus voltage rise and it will go more than reference voltage. Suppose 400 you have taken, it is going above the 400, around 405. This means there is large amount of power at the DC bus. And if battery is in SOC is less, so you can take the power from the DC bus to charge this particular battery. Now more shifting control. So this one I have already told you in the whiteboard, like we have to measure the voltage, frequency and phase. So using direct measurement, we can get the voltage magnitude, but frequency and phase are derived with the help of PL. And here VG max, and we have limitation. Here I have shown you in terms of VG max and VG minimum, FG max and FG minimum, and difference between theta grid and load theta. So these three parameters, if satisfying, they are satisfying, then we will go in grid connected mode. If these three parameters we are not satisfying, then system will be controlled in islanded mode. And these accordingly, the power electronic switches or STS, whatever you say, they will get 1 signal and 0 signal according to that control. And this is the flow chart for energy management. How we are going to managing the energy, because once you have bidirectional sources, so energy you have to manage the energy in that particular system. So what we have to do, we have to monitor the grid parameters. We have to see the condition that grid power is 0 or not. So if it is 0, so STS will be activated and system will be shifted to the island. We will monitor the parameter. If PG power is not 0, all the parameters are within the limit. So we will go to the grid connected mode. In grid connected mode, power will be shared among the battery, load and grid. And we have to check the condition that PV array power is more than the load or not. Means more than the load demand as well as the state of charge of the battery. If it is yes, then we have to check the SOC. If it is no, we will we will check the SOC of the battery. In both the cases, we have to check the SOC of the battery, because SOC of the battery is very important. How much power we have to feed or not. So SOC of the battery is greater than the SOC max. We will feed the surplus power to the utility grid, because battery is not means battery power is battery will not consume any power. If SOC is greater than the SOC minimum, we will feed the load from the utility grid, because we need to charge the battery here, and peak power saving will take place. We will charge the battery. However, in case of islanded mode, we will again check the PV power, we will check the SOC, and accordingly we will operate these battery in SOC max, off MPP mode, load shedding, feed the load till SOC max. So these 4 conditions will be satisfied according to the PV array power. Regulation of AC voltage, islanded control in DC bus voltage, these are the requirement during the islanded mode. DC bus voltage will be regulated through bidirectional converter. However, the PCC voltage will be regulated by the islanded control. So on this particular topology, this particular control, we have drawn the conclusion in terms of results and discussion. So here you can see that the results, simulated behavior of microgrid, single phase system is there, microgrid with buck boost controlled battery energy storage at certain outage and recovery of utility grid. So these are the angles which has been estimated using PLL, simple PLL, theta L, theta S, load voltage angle, load source means grid voltage angle. Then we have grid voltage, grid load voltage, grid current, load current. Here we have also considered non-linear load. And you won't believe, if we are going for simple synchronization, because ultimately your frequency theta, they are various these are the very the terms which are going to affected by frequency, affected by the high frequency switching noise or some non-linear current. These things will affect the value, because exact estimation of theta, exact estimation of frequency is very essential. Okay, these exact estimation is very essential. Otherwise, there will be a chattering. When you are going for on, it may be possible sometimes this, even though grid is available, your switch will get 0 signal. So some kind of on-off chattering kind of thing is happening in that theta, and we have realized in experimentally also this thing. So when it should be on, it should go into off mode. And so the synchronization process, islanding process is very much difficult when you have non-linear load at the point of common coupling. Because you need not to take care of one. As I told you, this is the multi-mode system. It will operate in both the modes. It will supply active power to the grid. It will also indicate, or it will also address the harmonic issue. You are drawing here nonlinear current, but here you will get the sinusoidal current. ISH sinusoidal. Here you can see. So till 0.4 second grid is there. After 0.4 second grid is not there. Suddenly there is disappearance in the grid. So here the grid voltage going to be 0, but the load voltage you can see, black one is the load voltage. So load voltage is maintained sinusoidal. There is no interruption across the load. Load power is constant. Load, there is no deflection, there is no change in the load current. Even though grid outage is there in figure A, in figure B you can realize there is synchronization or sudden appearance of the grid, or sudden grid is appeared, recovery of the grid is happened. So in both the mode there is no disturbance across the load, so load power is continuous. DC link voltage is also maintained to actual value. It is maintained to 400 volt. Battery voltage, we have taken a 240 volt battery. So 240 volt around voltage we have maintained. Battery current. Earlier it was in discharging mode, as we were considering that we can support the grid, there is load demand and all those things, peak load demand. So the battery current, you can see that above, it is above 0. So it is in discharging mode. And after that, after 0.4 second, when the system moves to the standalone mode, so we have enough supply from the PV array, and at that particular moment, now we can charge the battery which we have discharged earlier, so that the SOC of the battery can be maintained in the standalone mode also. Because we don't know, nighttime if grid disappears and PV array disappears, so we require the battery. So now in daytime we have considered the daytime scenario, and we have charge the battery so that we can maintain the SOC of the battery at that particular time. However, the PV array parameter, VPV and IPV, both are maintained. VPV and IPV, both are maintained here. These are the harmonic spectra, harmonic analysis for grid current and load current. So grid current harmonic, you can see that the total harmonic distortion is around 4.16%, and TSD of this particular waveform, load nonlinear waveform nonlinear current is around 31.6%. These are the steady state and outage of PV array. So under outage of PV array, what happened? Grid is there continuous, but certain outage of PV arrays happened. So if outage of PV arrays happened, so at that particular moment, what this power is reduced because load demand is reduced. I mean, load demand is constant, but earlier we were having net active power to the load as well as to the grid. Now grid, the power from the PV array is reduced. So this is the power after 0.3 second, which is required by the load only, which is required by the load. And after 0.3 second, there is sudden phase change. Earlier it was out of phase, but now it is in phase with the voltage. You can see this pink current, second plot as well as fourth plot. Till 0.3 second, both are in out of phase, which means power is injected to the utility. After 0.3 second, current and voltage both are in same phase, which means now load is drawing power from the utility, because PV array is not there obviously. And here we have considered that the battery in the floating mode, one more operation of the battery apart from the charging and discharging. Why we keep this battery in floating mode? We are thinking that the battery of the SOC is maintained above 80%. So third conclusion we have drawn, third consideration we have taken for this particular task. Now we will draw the thing like battery in the floating mode. Now the experimental verification. So experimental result using DSpace 1103 microlab box, DSpace 1103, DSpace space control. This is not a micro lab box. This is the 1103. And we have taken a solar PV emulator, that is Amitech based, and a battery bank of 21 ampere hour site make battery we have taken. We have taken MCB for creating the fault, because you have to create the fault toward the utility grid side to test your system. And semicron based DC to DC, DC to AC conversion unit we have taken for bidirectional converter, for voltage source converter unit. So this is the actual prototype which we have developed in the IT Delhi laboratory. We have array simulator here. We have DSpace 1103 sensor and optocoupler board. So sensor boards are dedicated to sense these parameters at the converter output at the grid side. However, these optocoupler are dedicated for creating the switching pulses for these converter. The converter here we have boost converter and for MPPT, and then we have voltage source converter. And this converter is dedicated, the converter at the right side is dedicated for bidirectional as well as for static transfer switches or static. So as I told you, simple IGBT we have used for static transfer switches. For STS we have taken simple IGBT, and one battery bank we have selected here. You can see the battery bank, you can see the nonlinear load diode bridge rectifier followed by RL we have taken as a load. And this is the MPPT performance. So percentage of MPPT tracking here, you can say that you can see that the MPPT percentage around more than 99%. It is in between 100% to 99%. And these are the experimental result. Sudden recovery of utility grid. So grid current appears. However, there is no interruption toward the load side. Suddenly, during the appearance of the grid, both the grid voltage as well as load voltage are well synchronized. Well synchronized. There is no any phase difference between them. And here you can see in third plot, third figure, third ESO picture, you can see that both the voltage and current are out of phase, which means during the recovery of utility grid, we are injecting power to the utility grid, and battery reaches to the from charging to floating mode. And at outage of utility grid, the grid voltage is gone to the zero. However, the phase frequency magnitude of load voltage is maintained throughout the process. Either we are operating in standalone mode or we are operating in grid connected mode. And suddenly as the voltage disappears, suddenly current disappears. However, battery moves to charging from the floating mode. These are the steady state result, constant power feeding mode when we have grid and we are feeding constant power to the grid. So around minus 2.34 kilowatt power we have injected to the utility grid, and TSD around 5%. However, the load current TSD is around 31.8%. And we have harmonics, I mean in the load. However, grid current is we have sinusoidal grid current. And these are the intermediate signal related to control. So we have observed the dynamic response of this particular circular normalized base current control is very good. And it is settling down the active component which we have derived. I mean within a cycle we are shifting. So dynamic performance in both the cases, like we don't have PV array as well as we don't have grid. So under this condition, what will happen? At outage of PV array, the grid current is reduced. Same we have seen in case of simulation, because here now we are feeding power to the load. So the load demand is less than the PV generation. So the current which is coming from the grid will be reduced. And at outage of PV array is not there. Suddenly grid is also disappear. So what will happen? Battery will be discharged. Battery is discharged now. And why this battery will be discharged? Because we have to support the load. The load power is continuous. Even your PV source is not there, your outage of means grid is not there. So battery will supply the load. Here battery, you can see that battery is discharged. Our load current is continuous. Load current is continuous. So we cannot disturb the local loads, emergency loads, we can say data centers, hospitals, or some other loads. And as the PV array recover, Again, we start power feeding to the grid, and battery, as a source of the battery is maintained, so still it is a floating mode. Now, this was all about single phase synchronized system. We have simple 3-phase system also. So 3 STS we have to use here. 3 static transfer switches we have to use. And we have again developed this topology, and we have published in IEEE Transaction Industrial Informatics in 2019. So this is the 3-phase topology along with battery and along with STS. And these are the design for 3-phase system which we have earlier seen. So control are categorized for 3-phase bidirectional control, and this boost converter STS both are same, but here we have different control for VSC as well as means operating in grid connected mode as well as in standalone mode. So again, we have taken some soft computing based technique as the dynamic response is good. SOC of the battery we have considered here, and we have considered the net active component. This way we have derived the active reference grid currents which are compared with the sense grid current to generate the switching pulses. However, in case of standalone mode, we have to generate the frequency reference. So these 3 voltages we have sensed: VLA, VLB, VLC, and these 3 voltages are compared with the actual voltage to get the current reference. These current reference are compared with the actual current to generate the pulses, 6 pulses, because IGBT we have taken. And this is the thing which I have not discussed for a single phase system. So here we have to regulate, or we have to reduce the error between theta grid and load theta. So PI controller is dedicated. So how many PI controller? One is for one is for DC bus voltage regulation. Another is for battery current regulation. Cascaded PI we have seen. Okay. So 2 PI controller for that one, and third one for reducing the error between theta L and theta G, phase angle of grid and phase voltage phase angle of load. So simultaneously we are controlling. So you can assume, or we can see that how it will be difficult to control 3 PI controller. People are getting sweating when they are controlling only 1 PI controller. Here we have control simultaneously. We have controlled 3 PI controller at a time. Phase angle PI controller, DC bus voltage regulation, and battery current regulation. Because in cascaded PI, inner current control was responsible to control the battery current. How the IB will be regulated, how the battery current will be regulated. So this way we have we got this error, theta error. This theta error is converted into frequency error. This frequency error is added with the actual frequency. And if again condition grid restores, so this loop will be operated. If grid outage is there, constant frequency we will supply in case of standalone. Constant frequency means we will get here 2 pi f, then we will integrate it, we will get the reference load voltages, that is VLA, VLB, VLC, VLA star, VLB star, and VLC star. So here we will get these reference load voltages in case of standalone. Again, same cascaded PI we have taken here. But for synchronization and desynchronization, or we can say synchronization islanding control, what we observe in single phase system, there is significant error, or the estimation of frequency and phase is not correct in case of PLL. So for reducing these demerit of PLL, we have taken enhanced phase lock loop for estimation of phase and frequency. So in case of PLL, what we observe, the magnitude as well as phase frequency are estimated within a single loop. We have single loop. If you read the Karimi book, you will find out what are the actual demerit of PLL and how we can proceed with the advanced PLL, some advanced PLL, how we can proceed. So for this purpose, because this, you can see this structure of EPLL, we have separate loop for amplitude section, if any harmonics is present in the VSA, so we can filter it out using amplitude section, and we will get the fundamental voltage. However, using this error between the fundamental and actual voltage, we will get the frequency and phase section. I mean, this error, using this error, we will estimate the actual frequency and phase. So this way we have got the correct information of phase and frequency. So in left side figure, you can see that grid voltage, load voltage are sensed, and we have estimated the magnitude, and using EPLL, we have derived the frequency as well as theta. We have taken the change in frequency, we have taken the theta error between theta grid and theta load. So, and after that we have monitor of 3 parameter, monitoring of VT, rate of change in frequency, and theta error. So all 3 quantity we will monitor. And after monitoring, what we will do, we'll be having, we will see that these things are within the limit or not. If these are in the limit, we will go for grid connected mode. If these are not in the limit, we will go for standalone mode. And this is the comparison between experimental comparison. Remember, it is not any software comparison. Actual, whatever the signal which is coming, we have sensed through PLL, and whatever the signal which is coming, we have sensed through PLL. So we find out that the frequency variation, frequency jump, phase jump. You can see the phase difference even when the system is connected. When the microgrid is connected with the utility grid. So what happened? We have various larger phase difference, and it may not follow 3° whatever we have given. However, the signal theta, which is estimated with the EPLL, they have less difference. And under connection, certain connection, chattering, you can see here the signal or theta which is estimated with the PLL. So these are the few differences why we are going for this PLL and EPLL. And then we have drawn certain result related to this particular thing, like simulated performance under certain outage of utility grid. We have seen how the battery is behaving, how the PV array parameter, how the VSC current. You can see the VSC current. VSC current till 0.4 second, it is carrying active power as well as harmonic power, but after 0.4 second, it is carrying only load power. Why? Because grid is not there. So the AC side we have only load. So it is equal to the load demand. Means 5 ampere current now it is going to the fed to the load. Sudden synchronization at 0.6 second. So under 6 second, we realize that VS grid voltage appears, grid current appears, and VSC now carrying the active power as well as harmonic power. And VDC and then bidirectional converter, this PV array current is also maintained, and then this DC bus voltage is also maintained. Then simulated performance under load unbalance. And the load unbalance, we have realized load is reduced, so net power fed to the grid is increased. And remember, this is the grid connected mode. So TSD we have shown, IEEE 519 it is following, and then we have IPV here, outage of IPV. So there is change in phase. Earlier it was out of phase. Here you can see you can consider one. So black one you can consider, and you can follow that black voltage and black current both are in opposite phase. However, after 0.4 second, black voltage and black current are in phase, which means now it is drawing power from the utility grid. And you can see the VSC current. Earlier it was having both the power, but after 0.4 second, it is having only harmonic power, which is required by the load. And these are the PV feed forward under increase and decrease. So for 3-phase, we have also developed this experimental prototype. We have verified, and under outage of grid, seamless transition of micro under outage of grid. So under outage, grid is not there, and this STS goes to 0. As the utility parameter are not in the prescribed limit, because magnitude is disappear, magnitude is gone to the 0. So this STS is also reduced to 0. The signal supplied to the STS, static switches. So 3-phase voltage also disappear, grid voltage. And under disappearance, we have this grid current also disappear. However, load voltage is maintained throughout the process. Battery is going to the charging mode here. And under restoration of the grid, when the system is restores, and so both the grid and grid current and grid voltage are in third figure, both are in opposite phase. Load current is maintained throughout the process. And these are the steady state performance and TSD of grid voltage. So under disturbance, there is polluted grid, 11% TSD is in the grid voltage and 22% in the current. So we have verified the system under polluted grid also. Means both the grid and grid current as well grid voltage and load current are polluted. So under this condition, we have synchronized our system and we have found out TSD of grid voltage and current found out within the limit of IEEE 519, which is less than 5%. And we have these waveform. First waveform, you can see how the grid voltage is deteriorating. After, after switching on the converter, after switching on the microgrid, these voltages are sinusoidal and balanced. And these are the results under outage of PV array and a sudden increase in the PV array. We have realized that this system is working perfectly fine. So outage of at 0 PV current, we have seen the outage of grid and recovery of utility grid. And we have also proposed a 4-wire synchronization, 4-wire synchronization for 4-wire system, extra 4 wires. So using only 3 static switches, static transfer switches or static switches we have derived, and this particular thing is published in November December issue in ATAL transaction and industry application. Recently we have published these papers. So again, this is categorized and this is the control under. So here neutral current we have also addressed because 4-wire topology is having major issue with the neutral current. So neutral current, you can see ISN, that is 0, and we have ILN, IVSC under synchronization and desynchronization mode. This topology is also under outage of grid and recovery of grid when grid is there, grid is not there. Load current, you can see that load current is continuous, but when the grid connected mode, so neutral is floating now, and we have realized that 4-wire topology having a square shaped current after recovery of utility grid. And these are the steady state where this little bit black line shows the neutral current. So 0.9 ampere current is in the neutral. However, here the black in D figure, you can realize the magnitude of neutral current is 2.7 around. So this way we have reduced the neutral current here, and you can see the neutral current supplied by the VSC. Same amount of current is supplied by VSC, 2.8 ampere current is supplied by the VSC. And these are the some results which we have drawn for 4-wire topology also. So we have a detailed investigation, synchronization, desynchronization for these thing, and these are the references related to this particular work. And if you want to discuss anything related to this one, now we will try to answer the question if time permits, I mean. And if you want to discuss further your research and anything related to this system, you can contact me on this mail ID. So thank you very much, and we can spare 15 to 20 minutes in question if there is any question, anything which people want to discuss with me. Over to you.
Thank you, sir.
Host.
Participants, any queries?
Thank you, sir, once again for your second wonderful session. Really, today also I enjoyed your session. I hope.
Yeah, thank you very much. Karthik Reddy, I think.
Yes, sir. Yes, sir.
Yeah,
In
thank
the
you.
last session also, I have interacted with you.
Yeah. In last session we have interaction. I mean, I've asked a couple of questions.
Sir, whenever I'm doing a literature review on this particular
Yes.
system, like you mentioned.
Yeah, can you speak loud little bit?
Okay. Yes, sure. Sir.
Yeah.
Sir, is it fine now?
Yeah, sure.
Okay, sir.
Mm.
Sir, in the literature review, I found that for the same system, like it may be a single stage with battery without or double stage without, they are
Yes.
proposing different control algorithms. So my doubt is how to identify a particular algorithm, sir. Like you said, soft computing techniques. You have mentioned like LMS or LP-norm or circular NLMS, different algorithms. So as a beginner, because I am at the beginning stage, suppose if I want to work on a particular system,
So that day also I told you, I mean, if you want to apply any soft computing based technique or adaptive filter, so first you can initiate with the LMS. Least mean square is the basic algorithm for this in this area. I mean, whenever you want to control your power electronics using soft computing based technique, so start with LMS only. If you are able to simulate LMS control, or you want to, if you are able to realize this LMS based control, you can apply any algorithm which is used for medical, I mean, for filtering the noise in the medical equipment. Okay, you can find out some paper related to medical equipment, okay, where they are applying these filter to filter out these harmonics. Okay, suppose I'm using one oscilloscope in the medical condition, or I'm monitoring heart rate. Okay, so they have some specific heart rate monitoring instrument. So these they are using some kind of filtering algorithm in that one. Okay, but that instrument is different, and that filter means component or filter are also different. So you can rely same way. Suppose we are having in our solar PV system, we are having some harmonics present at point of common coupling, and we want to realize, or we want to filter out these load harmonic using the algorithm which has been used for medical equipment. So your application is different, and the application, the filter which has been used for, or some soft computing technique which is used for by the medical researchers, or we can say the algorithm which has been used by the medical in the medical instrument, that same algorithm can be applied here. Okay, but you have to identify, you have to first think that how we can apply LMS, simple least mean square based algorithm, because here the controlling factor is only one. But when you will go for soft computing based technique, there are multiple factors which you need to regulate, or sometimes you will find the non-error also, and you will realize that I mean there are multiple factors which you need to tune. Because these factors are responsible to control the steady state as well as dynamic response. I mean, they will control the dynamic response of your system as well as steady state error, which is happening. Suppose second harmonic component is reflecting at the DC bus. So you have to control in such a way so that the minimum second harmonic component should be reflected at the DC bus. I hope I have answered your question.
yes, sir.
If you want to further discuss and you want basic papers related to LMS, you can write me mail, so I'll forward you.
Sure, sir. Thank you, sir.
Okay, thank you.
Hello, sir.
Yes, Gaurav.
Good afternoon,
Yeah,
sir.
good
So
afternoon.
my name is Gaurav Yadav.
Yeah.
Sir, I want to ask that the converter that you have showed, or you have used, that bidirectional converter in that battery.
Yes.
I want to know that the you have said that that is a buck boost converter. But
Yes, bidirectional buck boost converter.
yes, sir. Yes, sir. So I have a doubt, sir, that in the diagram that inductor is not in the middle one, but basically what I have been we have been known that in buck boost converter, inductor is in the middle leg, or in the middle uh, of a circuit diagram, in a circuit diagram.
Yeah,
But
exactly. It is in middle one. If you realized, I mean, You have not realized the picture. Let me show the PPT.
Yes, sir. I
Because
think it
you
is
have
on
seen
9
the
and
two
31.
switches. Huh?
Yes, sir. Sir, I have seen that.
Let me. Which PPT you are saying?
Sir, on the 9 and 31 page.
Okay,
On the slide, yes, sir.
31. So let me share this PPT. Okay. Yeah, this PPT. Are you getting? Hello?
Yes, sir. Yes, sir.
Yeah. So this inductor is not in the middle?
Yes, sir.
Huh?
Yes, sir.
How you can say that this is not in the middle? Now I have to
Because
draw.
I think I have just seen I have to analyze also. I think, sir, now I have to see it
Let me
where
draw
can should
the.
go.
Okay. So this whiteboard is visible?
Yes, sir. Yes, sir. It is visible.
Okay. So what I did, you might have seen this kind of picture. Switch to. So you might have seen this kind of picture. We have suppose DC bus here, and then we have bidirectional converter like this,
Yes, sir.
and inductor,
I think
and
now
then
now I
battery is
got it.
connected. Huh? Like this. This picture you have seen.
Yes, sir. Yes,
And
sir.
what I did, I have
I
drawn
think
a battery.
I get it,
Yeah.
sir. I
I
get
have
that.
drawn a battery. Yeah. And like that, we have drawn this figure. Means this is
Yes,
the
sir. Yes, sir.
multiple way which you can draw the figure.
Yes, sir. Yes, sir. Now
Hmm?
I got it.
Yeah.
At
So
that
this
time,
is the figure. So if you keep this one upside, so it will be
yeah,
in
yes,
middle.
sir. Yes, sir.
Hmm?
Understood.
Yeah.
Understood, sir.
Yeah. Yeah.
Thank you, sir. Thank you.
Yeah. Thank you. Yeah. Any other questions?
Yes, the participants, any more queries? Sir, they can write it to you for your mail in any
Yeah,
query.
sure,
Sending,
sure. I have shared the mail ID, and
yes, sir.
if they are having any doubt, they want to discuss any research, so they can write me. No issue.
Okay, okay.
Yeah.
Participant, if you have no any other queries, you can ask. Otherwise, we can. Sir, with your permission, can we?
Yeah, sure, sure.
Hi.
Can.
Sir, thank you, sir, once again for a very informative session. You have discussed PVBS microgrid system and its control in great detail, and all the participants have listened and viewed your presentation so diligently that they could even remember the page numbers that we have put in. Thank you so much, sir, for a nice presentation, sir, and it will greatly help the researchers who are working in this area and also students who are planning to work in this area. Thank you, sir, once again for spending a long time with us, like with 2 sessions you were with us.
Yeah.
So thank you once again, and thank you, sir.
Yeah, thank you very much. Thank you, Anil ji, as well as the organizers and NIT Manipur for providing me opportunity to conduct 2 sessions, which is, I mean, difficult as we have 2 hour session and all those things. So thank you very much. Thank you for this opportunity. I'm happy and yeah, I means as well as I would say that thank you to the participant, and they have carefully listened me, and yeah, they have spared their time, and means they have asked the questions query related to these systems, as well as, I mean, you can write also if you are facing any issue with these systems when you are going for simulation or going for literature review. So thank you once again.
Thank you, sir.
Thank you. So now can I leave?
Yes, sir. Yes.
Yeah, okay. Thank you.
Okay, the participants, the next session will be by Arnav, sir. So please join the session before 2:45. I think, yeah, before like around before 2:55. Yes. Thank you. Good evening, sir.
Good afternoon. Am I audible properly?
Yes, sir. Yes, sir.
Okay.
Sir, can we start our session, sir?
Sure. You please start. Yes.
Okay. Good evening, sir. Once again, I welcome you to this FDP program on recent trends of control systems and power electron converters. Yesterday afternoon session, you have talked about detailed details of modeling of DC-DC converters. You talked about types of controllers, type 1, type 2, type 3. You made a comparative analysis of boost, tri-state boost, interleaved boost, and cascade tri-interleaved boost converters. And now we are eagerly waiting for today's session, sir. So without taking much of your time, I will request you to take over the session, sir.
Thank you very much. Just for a moment, I am sharing my slide.
Okay, sir.
Is it visible?
Yes, sir.
Yes. Okay. So I hope my slide is full screen from your end. Am I right?
Yes, sir. Yes, sir. Yes, sir.
Okay. So very good afternoon. Okay, so all my dear participants and the session personnels, okay, as well as especially thank to Professor Minal Kanti Sharkar. So is asking me for requesting me for delivering some idea about it. So in my last presentations, okay, I was discussed about I discussing about different topologies of microgrids, converter, and integrations of that renewables to our microgrid system. So today my session is quite informative regarding. I'm going to discuss about different different topologies, not like exactly topologies, the brief idea about vehicles. Okay, means sustainable transportations in one word. Okay, so still that course is related to the power electronics and control. So there is a huge applications. Okay, there is a huge applications of different power electronics converters as well as control aspects. Okay, in our vehicular technology. Okay, so how they're related? Basically, you know that one very important points are there in electric vehicles, that is battery management system. Okay, so that we are talking about different controllers. So battery management system and sometimes hybrid storage management system. Okay, so you know that everything means storage in our microgrid system. Storage provides the reliability of the system. So you can consider that for our transportations. Okay, like sustainable transportation. So energy storage plays a key role. Okay, energy storage is playing the key role for driving the vehicles as well as the power management. The most important or most key features is that power management of the system. Okay, so power management, but by whom it will be done by it? So normally we are using BMS. Okay, so here we are going to discuss about very brief idea about the introductions and different challenges of the electric vehicles. Okay, so just like before starting the session, so what are the basic outline of our presentations? Okay, so that here we can see like that. So electric vehicles, like introductory portion. So why electric vehicle? Okay, so that's very important thing. So definitely there is some challenges. Okay, challenges in the field of vehicles. Okay, as well as the overview of the Indian scenario. So is it how much money is it compatible for our Indian scenario? As if it is not compatible, so what we need to do for it? Okay, so different of things, batteries for EV, then vehicle to grid and grid to vehicle charging. Okay, so basic green means basic idea we're giving Okay, so different protocols, charging protocol, charging infrastructure. What are the different types of charging infrastructures? Okay, especially charging stations are very important. Okay, some real-time applications. So basically, we can see here different. Here we can also discuss about basically how it will be look like that original charging stations. Okay, and different challenges is with the vehicles for the DC-DC converter topologies. But challenges are definitely everywhere. But we have to think about the aspects. Okay, how they are compatible with our system, how we are means implicable, how everything is implicable in our real-time system. That's our overall is very important issue. So first we are starting with that means why electric vehicles? Okay, so it's very common topic, so all of you are aware about it. Okay, so why electric vehicles? So you know that conventionals, if we think, if we see about the conventional vehicles, so basic problem is that pollution is the one of the problem, as well as fuel. Okay, so scarcity of the fuel. So that's why we can our technology. Okay, it's not like our technology. Okay, so overall technology is switched to the sustainable transportations. But if we go for the sustainable transportation, so there is a huge challenges. Okay, what are the different challenges? Number one challenges is that basically if we directly depends upon our sustainable resources, so what are the infrastructures in our country? That is most important issue. Okay, so I can recall my college days. So at that time, it's not a big time back, so more or less 10 years back. So I just saw that there is a small means you know that solar right now in our institute that street lighting is there. So battery fed street lighting in morning time means in daytime there is a panel is there. Panel is charging the battery, and that battery is means there is some light. They are taking the power from the battery. Okay, that was first thing I saw that installations. Okay, different places. So I just saw that some of the person there means they're thinking that it is their own property. Okay, so they are taking back their batteries, sometime panels. Okay, they're to the home. So that's why that ATC laws in our India. So we should very bother about that. How much cost efficient? So how the system means how our society are taking care about that infrastructure. That is another big challenges. Okay, suppose you can see if you are in Delhi, okay, if you are in Delhi or Bangalore or Hyderabad, in you know that right now that Ola having a huge hub in Pune, I think so, as well as your Mumbai. So different. I'm not talking about Kolkata. Basically, Kolkata there is not so much charging infrastructure till now. Okay, it's a very blooming, means growing stage. Okay, but this infrastructure you can see if you go to Delhi, so you can see there's everywhere pumps, the CNG pumps are there. Okay, so most of the four-wheelers, okay, they're converted to CNG. Okay, so but in other cities, if you go to the Kolkata, so you cannot see like that. I just heard about only two petrol pumps are there in Kolkata. They are only they cannot you can refill your vehicle CNG vehicles refill from that pump. Okay, but that's why I'm telling about you the infrastructures. Okay, so but if you go to Delhi, so you can see there is a you can observe that a lot of charging infrastructures are there. Okay, different startup companies are there. Okay, so few years back, not few years back, 2020. Okay, so more or less 2 years back, I went to an that means programs. Okay, so I just attended the course where I just saw that a lot of startup companies are there. Okay, so they're manufacturing the vehicles. Okay, so it's not like that they're all are manufacturing the four-wheelers. No, most of them are manufacturing the two-wheelers, and all are the indigenous company. Okay, so, but problem is that they're manufacturing the vehicles, but the most important components, okay, they're means exporting from, sorry, they're bringing from different countries, mostly China. Okay, so the technology that whatever they're using, the technology maybe they are manufacturing here. Okay, so but the technology they are taking care, I mean, they are utilizing, that is coming from, that means that is outsourcing from other places. Okay, so and they don't bother about that, about don't bother about the technology. They're only thinking about that how now this field is very growing. Okay, so growing, this is very growing field, so all are trying to be established in their fields. Okay, so in this discussion we are going to be discuss about not like only charging infrastructures, means it's not like that you are charging your vehicle. So in backhand, okay, backhand different softwares are there. Okay, how they are, if you want to charge your vehicles, how they are taking care about everything. Okay, so that I am going to discuss also here. Okay, so but what are the main challenges for us? Okay, so that scenario is important. Suppose you want to travel from Hyderabad to Delhi. Okay, so you are having one vehicles. Okay, electric vehicles. But main problem is that in your Hyderabad you can have you are having some charging infrastructure. Delhi also having charging infrastructure. That, but the distance between Hyderabad and Delhi, so it's more than 1,000 kilometers. So how do you charging your vehicles? That the big challenge. Okay. So that in that presentation is mainly focused on that how the charging infrastructures. Okay. What are the most important features for the charging? What are the different types of chargings are available? Okay, so what are the different government fundings are there for developing the infrastructures of the vehicular infrastructure, developing the vehicular infrastructure from our end. So that is our basic motivations for this presentation. Okay, so so here we can see that that another big important issue that that Paris, sorry, so that Paris Agreement. Okay, so a few years back, okay, so a few years back that was very popular because of what? Because of US US President Donald Trump. Okay, so he was there just coming back or coming running out from the Paris Agreement. Okay, so what was that agreement? That agreement, India took some oath that by 2030 they are going to be reduce the temperature value by 2 degrees. Okay, and as they are taking initiative. Okay, why that all the government schemes are in the direction, in the dimension of sustainable mobility, sustainable in the microgrid concept, smart grid concept. Why governments are promoting all of us? So few years back, so I think before COVID, government was taking initiative. So by 2022, they are going to ban all the petrol vehicles. Okay, not necessarily, means basically that city riding. Okay, for the means for urban riding. So they're thinking like that. For two wheeler, they are totally bans for that fuel. Okay, means conventional fuel based vehicles, especially two wheeler, three wheelers. Okay, so but due to COVID, that scheme quite now delayed. Okay, but after that, the BS6 is there already. Okay, so there is some comparison between BS6 vehicle and electric vehicle in the slides. Okay, so we can also discussing what money, which one is more convenient. Okay, so as if you want to reduce the temperature, overall temperature, so you have to take some initiative. So what are the most important initiative? That conservations. Okay, so preservations of the means conservations of your natural resources like water, forest. Okay, these are the very common issues. Okay, then utilizations of your renewables. Okay, so definitely it's very important. So if you depends everything on your conventional fuels. Okay, so it is definitely after few years the conventional fuels are not there, but demand of energy definitely day by day it is increasing. So who will take care about that overall demands? Means definitely you have to you have to think about your alternate source of energy. Okay, so renewables is only options. Okay, how efficiently you are extracting the powers from the renewables, that is important issue. So most of the research dimension is in your renewables. Okay, and how efficiently you are collecting the or you are collecting the power energy from the renewables. That is very important. Okay, then energy utilizations of your energy. Okay, so what are the energy that you are utilizing the energy mix? What is that? So now you know that initially for illumination purpose we're using fluorescent lamp. Okay, then CFL has came. Then after that, you know, right now that LED lamps are there. Okay, so that wattage. So okay, fluorescent lamp wattage is more or less 40 watt. Okay, after that 20 watt fluorescent lamp also be available. Then CFL is there 20-25 watt. Okay, now directly we are getting that LED lamp. Okay, so you can get one 10 watt LED, 10 to 12 watt LED that can giving more or less same illuminations like 40 watt fluorescent lamp. Okay, so that smart technology is there. Okay, smart and advanced technology is there for minimizing that utilizations of the energy. That is important thing, that utilization. Then buildings are there so smart. Yesterday I discussed about that how the microgrids also related to our building management system. Okay, then transportations is very important features. Okay, so in transportation sector a lot of works are going on. Okay, so by using the renewables as well as basically, you know, recently Tesla has launched a machine. So basically it happens in different sector. There is some innovations in your research in your power electronics converter system. That is one of the good idea for the transportation. Then driving systems. Driving system means who are responsible for the driving. Definitely different machines are there. Okay, some good research maybe work on that machine. So in single word you can say like that, the drive. Okay, the sustainable drives is very important. Drive train, okay, then battery pack drive trains, all are very important for our sustainable transportations. Okay, and the finally that we are not talking about more about that waste. Okay, that waste is very important issue, that waste management system. Basically, you know that if everything is there, okay, suppose you can consider that all the things is converted to all the things are now converted to sustainable technology. Okay, so but waste if definitely will be there. Okay, but that's handling the waste is the big issue. Suppose we are using the batteries. Okay, maybe lead acid battery, maybe lithium ion battery, whatever different types of battery you are using for our transportations or storage system. Okay, then battery having some life cycle. Okay, after that what happened? Okay, so reusable battery definitely is very important. And why the problem is there, you can see lead acid means lead is there, lithium ion lithium is there. Okay, then in that case you can see most of the cases the battery is using that heavy metals are there. Okay, so you cannot directly drain them after their life cycle. You cannot directly drain them in your local drainage system. Okay, then what happens if you drain them there? So directly it will come to the soil, and from the soil automatically it is come to our body. There is a huge pollutions. It may be the huge pollutions, and that may having huge effect to our definitely to that can give the huge challenges for the human civilizations. Okay, so that's like the waste management, how you are recycle them, and after its cycle, how after the completion of the cycle, how do you dump means everything is very important. So waste management are the very important sector for that one. So if you manage all those things, so definitely not like only 2030, so you can reduce the overall temperature. Okay, overall temperature from our end. Okay, so by that one, so India has launched a national action plan on the climate change. Okay, these all are the points for the proposed scheme. Okay, so after that you can see here. Okay, so here we can see some air pollutions. Okay, so air pollution index. So in India, so you can see that air pollution, so percentage wise, so most of the pollution is coming from transportation system. Okay, transportation system, then domestic pollutions also be there, domestic, then industry, then commercials and others. Okay, percentages they given, and agricultural pollution. So definitely you can see that from the transportation sector, more pollutions are there. So there's a huge scope of research work in the transportation sector. Okay, so how do you reducing that? Reducing the emissions from the transportation. So you have two options for incorporating that vehicles. Okay, so fuel efficiency and with having some advanced designing of your vehicles, advanced designing metals and technologies for the vehicles. Here you can see one comparisons. So very important cities of our India having more pollutions. Okay, you can see the ppm. Okay, so that we are before Diwali, before festive season, we are talking about ppm. Okay, so in our means floating particle. Okay, floating particle of our air density, air pollution index. Okay, so we are considering, we are talking about that. Okay, so you can see in that compared to that floating particles, you can observe that different cities, renowned cities of our India is always ahead from the different capital of China and different important cities of the China. Okay, so from that diagram we can understand. Okay, the common cases we can understand. So how it is important to convert all the system for the sustainable transportation. So here we can see some diagram. Okay, so from the diagram, so in this diagram is taken in the New York. So here you can see most of the carts are there. Okay, that is horse driven cart. Only one electric cart is there. Just after 100 years, okay, just after 100 years, you can see all are in automated card. Okay, automated vehicles except one card. So you can see the technology how it is changing from one generation to another generations. uh, so you can see from that picture. Okay, but main problem is that if that vehicles are launching in our field, so here you can see that waste that I am telling you. So that a lot of vehicles you can see they are dumping. Okay, so how you are able to use them? Okay, recycle is the important issue, and how you are dumping them, that also very important issue. Okay, so what are the most fundamental components for the charging, and what are the most important features of the charging? Okay, so here you can see, so on four-wheeler vehicles are there. Okay, so four-wheeler vehicles. So what are the most importance for the vehicle? So one charging pole is there. Okay, so there are different levels of charging: level one charging, level two charging. Okay, so I'm coming. What are the level one? What is level one charging, level two charging? Everything I'm coming one by one. Suppose it's an AC charging pole. So all are very aware about mg hectare. Okay, so now few days back some months back, so I saw it in different in television. I can see that given advertisement of the NG hectare. So what we can see, so it's having some charging stations, so charging poles are there. So from that pole, what we will do directly, you have to take that power to feed it to your system. Okay, so there is a onboard charger, onboard charger. Okay, offboard charger. Okay, what is onboard charger and what is offboard charger? Okay, so that we need to know first. Okay, so you have the storage battery pack is mandate components for the vehicles. Okay, so battery pack means you are charging the battery pack. Okay, so definitely you have to depends on the bidirectional converter. So normally what happens, the battery is charging in DC. Okay, so from here you are getting it from the AC value. So what you need to do, you have to convert that AC to DC. Okay, so for why you need to convert it? If you don't convert that AC to DC value, so you are not able to charge your battery. Okay, so charge for the charging purpose, definitely one conversion is required. So if that conversions, that AC to DC conversion happen inside of the vehicle, so you can say like that, it is onboard charger. But if you see, if you in your home, if you have your buying, okay, different electric vehicles are there, means two-wheeler, okay, city ride two-wheelers are there. You can see small board is there. Okay, so you are carrying that board and plug point is there. After that small board, then that board is coming to your vehicles. Okay, so that board is called, it's a converting unit. Okay, that convert the AC to DC. So our home, we are what about our home? So it is 230 volt AC is there. Okay, so we are charging when that electric vehicle, two-wheeler electric vehicle. So one small board is there. Okay, so that convert that AC to DC, and that board is outside of your vehicles. That's why it is called onboard charger. Okay, so here you can see that AC is there. Okay, so AC charging pole is there, level 1, level 2 charging. So normally it is coming 415 volt. Okay, so ampere also sometimes high. Okay, voltage is high means ampere level is less. Ampere level is high means voltage definitely will be less. Okay, so normally 15 kilowatt. Here you can see if it is 3.3 to 6.6 kilowatt chargings are there. So here AC is there, so definitely it should be converted to DC. That's why it is written that AC DC onboard charger. Okay, so the rating of that converter is more or less 3.3 to 6.6 kilowatt. Okay, you are converting them. Okay, then after that, what happened? DC-DC auxiliary power modules are there. Okay, so DC-DC auxiliary power module, what is the function of this? So it can, you can see there is a battery pack. Battery pack is connected just below of your sitting arrangement. Okay, so definitely the battery will be charging or sometimes discharging. Okay, charging and discharging. Okay, sometimes it's based on the demands. Okay, based on the demands. So definitely the DC-DC power modules are required. Okay, DC-DC power modules, and the rating of that converter is more or less 1 kilowatt to 47 kilowatts based on the utility. Okay, so then what happened? Then internal electricity, or there are a lot of driving units are there. Suppose AC is there, suppose power demands. Okay, internal power consumptions are there. Sometimes you are running the AC. Okay, sometimes you are playing the music. Okay, so different other sources are there required for doing some auxiliary work. Okay, so definitely that DC need to be converted again AC for playing all those appliances. So here we are using DC-AC auxiliary inverters. Okay, so that rating is almost 1.5 kilowatt to 2 kilowatts. Okay, for that purpose, for internal electricity and internal, sorry, you say like that internal internal appliance for running the internal appliances. Okay, so suspension also important, suspension control. So this is the basic structure. Okay, this is all the basic structure of what are the different types of converters are using in your vehicular system. Okay, so then here you can see the what are the different government policies. Okay, so why government is so much bothered about it? So if you see some graph, this graph is there. It is number of four-wheelers vehicles in thousands. Okay, 2020 it was in 15,000 in India. Okay, but 2019 you can see it is coming 7,064,000. So you can understand. So its percentage. Okay, so if you can see that for 71 times multiplications. Okay, in this 10 years approximately, that demand is so much high. So exponentially it is rising up. So that's why governments are taking sincere thinking, governments having sincere thinking to provide, okay, to provide that sorry, the basic infrastructure for electric vehicles. Okay, you can also see those are giving tax, they can also understand. So in the IT returns there is also governments having some schemes. Okay, the governments also giving some incentive. If you have any vehicles, or if you are giving some invest for the vehicles, you will get some benefits from government's end. Okay, so government also promoting so for utilizing that sustainable transportations. Okay, so what are the things you can see that decreasing, what kinds of infrastructures governments are promoting to manufacturers. Okay, promoting to manufacturers means that I am telling that lot of startup companies are there. Okay, you know that government having very good opportunity that is called the Startup India. Okay, so that this financial year also they are investing huge amount of money for the Startup India. Okay, so that's a lot of startup companies are there. Okay, why they are getting interest for manufacturing the vehicles? Basically, government's also taking some other initiative, like they are also trying to reduce the cost of different essential materials of that storage. Okay, so in vehicles normally we are using lipo batteries. Okay, or in lithium ions batteries. So they're what they're doing, they're decreasing the cost of that lithium ion batteries. Then what are they taking? Some strong policies are taking. So initial days there is a FAME. Okay, so FAME was there. Okay, so FAME 2 is right now is going on. So 10,000 crore. Okay, government also giving more or less 10,000 crore for that invest. Okay, for the investment of the FAME 2. FAME 2 is going on actually. Okay, so different fundings also be provided by the government. Okay, so for the facilitated that electric vehicles for our for our sustainable transportations. Okay, so different national scheme that provides the incentives for vehicle as well as charging infrastructure. What are the why that is important? So within India, government has set out the facilitate the framework to drive adoptions. Okay, so here you can see like that national scheme for provide the incentive charging infrastructure. Okay, then state policy framework also be there. Okay, those are very developed state. So in India, so all states are not so equally developed. Those are developed state and those having some good prospect of that sustainable transportations. In West Bengal, you can see that there is a huge applications of vehicles. Normally, you know that is known as Toto. Okay, so it's a battery drive vehicles. Okay, battery drive car. Okay, you can use in your city ride or goods carrier. But you can in our country, in our sorry, in our state, Odisha, so we cannot see such type of vehicles. Okay, so based on that state policy. Okay, so different states are taking different policies. Okay, so it based on their perspective. Then EV tariff for the 17 state that are published. So different tariff levels also be there. Okay, initially what happened? You need not to register it for to your local municipality. Okay, or the notified area or municipal corporation area. But now different schemes are coming, so you have to notify them. So that we are having some vehicles. What are the numbers are there? Okay, that is very important and very popular. Okay, so what are the different important policies? So means that I am telling that governments also promoting for giving incentive to the local persons. Okay, so what are that incentives demand by reducing the effective cost of the ownership? Okay, so definitely you are getting some tax benefit from there. So creating the supply to increase the availability of the EV models. Okay, also promoting different companies. Okay, so different companies to launch different electric vehicles. Basically, they are launching hybrid vehicles right now. In our institute, I can see initially a lot of conventional vehicles are there. Now, recently, I just saw a lot of person there purchasing their vehicles that all are hybrid in nature. Okay, that all are hybrid in nature. Okay, so developing charging infrastructure to alternate to alleviate range anxiety. Okay, so charging infrastructure you have to develop. Otherwise, what happen? You cannot ride from different city. Okay, so that's why it is very important. Okay, so here you can see for e-mobility regulations in India. So as per the guideline, as per the standard, government have developing some standard for or categorize them. Okay, so for why that categorization is required for developing the structures. Okay, suppose you have four-wheeler vehicles. Okay, some of the person having two-wheeler vehicles, some of the person having e-rickshaw, that is called three-wheeler vehicles. So all are electric vehicles, but they should not in the same category. Why they should not in the same category? Basically, they are rating. Okay, some of the vehicles you can say like that it is less than 2 kilowatt range. Okay, some of the vehicles are there more than 10 kilowatt range. So 10 kilowatt range, 2 kilowatt range, both the cases the charging infrastructure is not same. Okay, so when you are installing that charging stations, okay, so multiple options should be there. Okay, suppose you are not doing the same priority for those having city ride, those are having city ride or bike, e-bike is there. Okay, and some of the person having four-wheeler. Okay, so both should not be equally prioritized. they are not getting equal priority. Okay, so definitely some changes are there. So based on their standardization has been fixed up by the government. So suppose electric vehicles are there, they are giving some standard AIS 038, 039, different numbers are there. Okay, based on their rating. Okay, then HEV means hybrid electric vehicles. They are into category AIS 102, 1 and 2. Retrofit means okay, different retro drives are there, 132 parts they are giving. Charging station specifications, okay, they are giving AIS 138 part 1, part 2, ISO 170. It is international standard. Okay. Small series AIS also be there. Okay, low speed two-wheelers. Okay, you know like that two-wheeler having that electric bikes two-wheeler having speed up to 40 kilometer per hour. Okay, suppose 25 to 40 kilometer in between. Okay, it having some for this one you need not to get for license. Okay, if that is more than, you know that some vehicles are already there, they can compete with with Activa or Aviator or Maestro. Okay, in TVS that is, you know, that Jupiters. Okay, their range is more or less around 80 kilometer per hour and more than that. So for that one, same AIS is not there. So definitely that is high speed vehicles. Okay, high speed and high power vehicles. Okay, and for this one you need to register. You should have some license, vehicle license is required, otherwise you cannot drive them. Okay, then e-rickshaw, e-cart is there. Okay, so that is say GSR 709, GSR 2590. Then battery safety, so that you are installing the battery inside of your vehicle and now you are riding that vehicles. Okay, so there is a chances for the explosions. Okay, so all the cases that standardization is needed. Okay, protocols and standardization. Okay, so we have to follow the protocols, and India having some labs. Okay, they are providing that standardizations, and you go to that lab to standardize your vehicle also. Okay, so these all are the basic infrastructures or regulations or specifications of the protocol for your vehicles. So now I am going to discuss about what are the most common or most popular schemes. Okay, that government is that schemes are there for running that or for you say like that uh, for developing the infrastructures of your charging stations and vehicles. Okay, so who is that company? So normally Ministry of Heavy Industry and Public Enterprise. There, you know, that Department of Heavy Industry. Okay, DHI. Okay, they're launching different concept that basically that companies are main focused about electric vehicles. That is FAME 1. Different schemes are there, FAME 1 and FAME 2. Okay, so FAME 1 was there that approximately cost is 895 crores for demanding the incentive charging infrastructure, pilot project, etc. But what are the problem in FAME 1 that I told you before starting, just before beginning of the presentation. So I just made them and they are telling that they are manufacturing the vehicles, but BMS, I see that microcontroller, the controlling unit, all the things they are procuring from or outsourcing from China. Okay, so the product maybe look like indigenous, but main processing unit, brain of that product is not indigenous. Okay, so government pick that points and they are investing. So if, and launch that FAME 2 and investing more price in the head of two-wheeler, three-wheeler instead of four-wheeler, and the battery car drives. You say like that battery train. Okay, so they are giving more fund for it, and they are also giving the trust that the IC should be indigenous. If you are using, if anybody, any startup is using that outsourcing IC, so they will not get funded. Okay, so that's very important step. Okay, otherwise in the government fund will be outsourced to the other country. So that is not the motivation. That's a positive sign of this one. So that's why FAME 2 has launched with having almost more than 10 times. Okay, more than 10 times budget compared to the FAME 1. Basically, FAME 1 was successful. Okay, very successful. So that's why FAME 2 has launched. Okay, so funding agency that as I am telling that DHI is most important funding agency. Then Ministry of Powers also be there. They're also funding that mobility portions. Ministry of Finance, so they are also giving subsidy. Okay, giving subsidy to cost money, reducing the cost of that vehicles. Basically, initially the vehicle cost is very high, so definitely government should give some subsidy. So from Ministry of Finance is taking care about all the subsidy, okay, as well as some incentive given to the common person, those are using the vehicles. Okay, so these kinds of things are there, and Ministry of Road Transport Authority, so what they are doing, they are not exempt. Okay, exempt the costing of your, suppose you are riding the vehicles and you are traveling in national highways authorities of India, so they are not taking the charges from your charges, they are not, they can okay, waive out your charge. Okay, or you say like that, they can exempt your charge. Okay, so battery operated cart or methanol powered vehicles like that. Okay, so that's a basic important concept was there. So here you can see the FAME 1. Okay, so in FAME 1 you can see, sorry, FAME 2 scheme, what is there. Okay, so demand incentive was there 8,596 crore. So most of the thing you can see out of 10,000 crore. Okay, so they are investing. Okay, they are investing almost to 2,000 crore for the development, the charging infrastructure and the manufacturing of the two-wheelers. Okay, and 2,500 for the three-wheelers. Comparatively less amount of cost they are investing for four-wheelers. Okay, four-wheelers and the electric buses, they are giving that drivetrain. I am telling about it. That electric buses, they are investing huge cost. Okay, so that's why you can see all the companies right now, all the companies in India, those are manufacturing that vehicles, they are now manufacturing the electric vehicles. Basically, the vehicles company designing, suppose big buses designed by the Ashok Leyland, okay, Tata, they are giving more trust on that infrastructure provided, sorry, bus charging station for the bus. Charging infrastructure giving almost 1,000 crore. Okay, these all are the basic concept of the FAME 2 and how much cost they have invested for it. Okay, and that battery size cost was there. Okay, so demand incentive based on the battery size. Okay, rate was 20,000 per kilowatt hour. Now bus for the buses and 10,000 per kilowatt hour for the vehicle segments. Okay, these all are the guessing. These all are the invested power for it. Okay, so they are giving some target. Okay, this amount of target you have to provide. Okay, so different, that standalone system. Okay, and infrastructures of the standalone system, everything was means infrastructure of the charging stations. Okay, they are all are related to each other. Okay, so here we can see different. Here we can see different charging infrastructures guidelines. Okay, what are the different type of charging infrastructure? So we can categorize the charging infrastructure in two parts. One is called fast charging, another one is slow or medium charging. Okay, so for the fast charging, you know that combined charging stations, okay, CCS, okay, and its range is almost 50 kilowatt and 50 kilowatt, and voltage rating is on voltage rating you can vary like 200 to 700 watt. Okay, sorry, 700 voltage, and you are using for one connector guns. Okay, guns means from the charging port. Okay, charging terminal, directly you can connect the charging terminal from the charging panel or that pole to your system. Okay, so four-wheelers, you can see two different size CCS charger, Cademo charger. CCS is only popular for US, okay, US, Europe, and Cademo is normally very renowned and popular for Japan. It's Japanese technology, more or less the same. Okay, so Cademo charger. Another one is Type 2 charger. Type 2 charger means AC minimum 22 kilowatts. So here you can see the rating of that vehicles. Okay, 50 kilowatts. CCS chargers are very much popular for 50 kilowatt. Okay, and Type 2 AC charging, that is 22 kilowatt minimum. Okay, then slow charging, these all are the fast charging. Okay, these all are the fast charging, and you can see the voltage level. Okay, so you can also see the current level. If it is 50 kilowatt and voltage level is 200 or 750. So how much current level you can also calculate from that one. Okay, then slower chargers or moderate chargers. So Bharat charger is there, Bharat DC 001, DC 001 Bharat. Okay, another one is Bharat AC 001. These three are the slow chargers. Okay, so in this case, slow chargers, the voltage rating, okay, based on the rating, it is separated. 15 kilowatt, both of them, and another one is 10 kilowatt. 15 kilowatt, this is for four-wheeler, three-wheeler, two-wheeler, that is 48 volt. Okay, so current you can also calculate. Okay, so then another one is 72 kilowatt or higher than it, or it is four-wheeler system. And AC charger that I'm telling, Bharat slow charger. So for the two-wheeler in your domestic purpose that I'm telling about, talking about your bike. So you are connecting them. So directly it is 230 volt for the AC charger. Okay. So this is more or less you can connect it for four-wheeler, three-wheeler, two-wheeler as per your requirement. Okay, so here we can see the basic charging infrastructure of that vehicles. Okay, so from the structure, there is a basic EV. There is a very basic of EV charging stations. Okay, where you can see over there it's a AC charging and the DC charging. So one is onboard charger, another one is onboard charger. So onboard charger for the AC charging, what happened? You are giving the AC power to your vehicles. Okay. So if you are giving the AC power to the vehicle, so definitely that AC need to convert in DC. Okay. After conversions in the DC, then you can connect that DC to charging your battery of charging your vehicle battery. Okay. So if you doing that charging your vehicle battery, so lithium ion battery, whatever you are using, so lithium ion battery is quite costly. Lithium ion batteries are there, and then BMS is there, BMS battery management system, that how do you manage, so which how optimally you can connect your system. Otherwise battery life may be spoiled. Okay, so that's why battery management system is very important for that vehicle. So for the AC charging, the onboard chargers is required. For the DC, what happened, whatever charging supply is there, input definitely is AC. Okay, it's in substations. Okay, you have already converted that AC to DC. So inside of the car, no need to connect that conversions for AC to DC conversions. No need to incorporate any converter for AC to DC. Okay, so directly you can connect your DC charging wire to your system or to your vehicles. So there is no not any boards are not required. Okay, so that's why there is weight definitely will be less. Okay, compared to the previous one. Okay, so every vehicle need to have his own onboard equipment for the AC charging infrastructure. For DC charging infrastructure investment is shared with the hundreds of the user. Basically, DC charging, what happened? Different, it's your charging stations. So you are using only the infrastructure for the charging purpose. Okay, you need not to pay for that onboard charging station. Okay, and that charging unit may be utilized by the other person also. Those are booking the slot for charging their vehicles, they can also use it. Okay, so no additional things are so what happened, you will get some benefit over there. Okay, and that charging infrastructure will be utilized with other person also. Okay, so here we can see the topical layout of the electric vehicle charging station. Okay, so suppose you can talk like that, a grid. Okay, some grid is there. Okay, so onboard charging, offboard charging. So offboard charging, you can see it's look like a charging station. Directly that plugs are there. Okay, gun. It is called gun. Directly you connect the gun to your battery. Okay, so for onboard charging means level 1 charging, and offboard charging means onboard charging level 2. Okay, onboard charging two types, level 1, level 2, and for offboard charging it is fast charging, that is fast charging method. Okay, directly your vehicles are there, you are connecting your gun to the vehicles. Okay, so suppose onboard charging AC to DC conversions is required, basically it is AC. Okay, directly you are connecting the AC to the system. Now we have that converter, that that input is required input is DC. So again you need to convert that AC to DC. So AC-DC converter is required. Then you can see the PFC, power factor corrected converter. Basically, in that case, you can see there is a power electronics, lot of power electronics converters are there. So that may affect to the power quality. Okay, that may affect to the and that may create the issues for the power quality. Okay, so what you need to do, you have to mitigate that issue. Okay, so you have to remove that issue. That's why you are using the PFC converter. So that make your voltage and current in phase. Okay, and try to reduce the harmonics. Okay, then that DC-DC converter is there after conversion. Okay, then DC-DC converter is fed to the DC link capacitor, and DC link capacitor the directly AC to DC converter. Basically that motor is the driving motor, if it is induction motor or AC motor. So definitely again that on inverter is required to drive that motor, so or to convert the DC to AC. Okay, and that if there is inverter, okay, so you can use the different sophisticated topologies of the inverter. Okay, NPC inverter you can use, or you can also use multi-level inverter. So which one provides you better PhD value, okay, or a better quality of the power, that you need to use. Okay, as well as the simplicity of the control. If you want to control the speed of that motor, so definitely that inverter, that DC-AC converter or inverter broadly known as, so that need to be controlled. Okay, so everything will be controlled by your control logic what you have developed, and battery pack also be there for maintaining the DC voltage constant. That grid voltage is there, so capacitor is there, that capacitor maintaining the grid voltage. So battery pack is always try to maintain that grid voltage or internal bus voltage of your vehicle. Okay, so after balancing the after balancing that voltage, so directly you can feed it to your DC-AC converter, and that AC converter and that AC you can drive your motor. Motor can be driven by that AC. Okay. So here you can see, if you consider for some renewables to your system, so that need to be connected to the rooftop of your vehicles. Okay, so here you can see in the different structure of the vehicle, so rooftop solar is there. Okay, so sometimes that solar is also able to responsible for charging the battery pack. Okay, so battery pack is normally situated just so below of your sitting arrangement and backside of your sitting arrangement. Okay, so here you can see that battery pack is connected over there. Okay, and you can see that cord for the charging purpose. Okay, cord is there for the charging purpose. So battery packs are there, battery management system. Okay, so when a battery management system means how optimally situated the battery, how much number of batteries are required. If there is a super capacitor, so total number of the super capacitor. Now combinations of battery and super capacitor for this amount of rating, what will be the number? Okay, everything is required. Okay, then high voltage electric cable. So that high current is flowing through this path. So voltage is moderately high means, so compared to the high current, so definitely high voltage sometimes is current, but high voltage is there. Okay, so everything should be withstood by this conductor. Okay, and transmission and the electric engine. So then what happened? And power electronics converters are there. So after getting the voltage, so how efficient you are transferring the power from one side to another side, that is also very important. Okay, efficient conversions or efficient and sending, sorry, that power should be sending from one side to another side and very efficiently. Okay, that's why some power electronics converter obviously required, so that can convert the power, so whatever your requirement. Okay, if your requirement is DC or if your requirement is AC, so different types of converters or different topologies of the converter you have to incorporate over there to controlling the transmission of the electric machines. Okay, so machines are there. So machine is responsible for movement of the vehicle. So from where you will get the power? So from that storage. Sometimes storage is there. From the storage you are getting that power to drive your vehicles, or sometimes sustainable sources you are using. Okay, so from where directly power is coming. Okay, so based on your situation, you can think or conclude about it point. So what are the most important and features or more important components are there for the vehicular technology? First one is the charger. Okay, so you need to know about it. So it is onboard charger or offboard chargers. Okay, if it is onboard charger, so what kinds of power you need to feed to the how much power you need to the feed to the system, and if it is offboard charger, so which type of power you need to give to the system. Then batteries, the rating of the batteries, what are the different types of the battery, what are the manufacturing unit of the battery, what are the ingredients of the battery. So everything is required. Number three is that controller, that management controller. So if the vehicles are there, so what you need to do, and how do you control that vehicle speed. Okay, so then how that power will be managed to your vehicles. Okay, from input side to from source side to load side, everything will be taken care about your controllers. Okay, then after controllers, here you can see some port box. Okay, here you can see some port box that can convert the motion of your toggle paddle. Okay, paddle into an electrical signal for the controller. Okay, so whatever signals are you are providing, it can collect and convert for the suitable configurations. Okay, then motor is very important. Which type of motor you are using, and based on that you have to design your vehicles. Okay, and based on that you can design your speed of the how much speed it can maximum you can reach. Okay, how fast you are reach those amount of speed, everything will be decided by that, which motor you are using. Then transmission, so motor is developing, then what happened, that value is transmitted. Okay, so transmission and the efficiently transmissions. Okay, so without having any loss. Okay, that is very important. So coupling of your motor to that system. Okay, then main contactor, so different contacts are there, means isolated type of thing. Okay, so when you are connecting your vehicle to the grid. Okay, so you have to connect that wire to directly to that vehicles. Okay, so that's very important, how much how efficiently you are able to do this. Okay, so emergency disconnect, or even before that one, that instrumentation. So okay, so regularly you have to monitor all the parameters. Okay, so as that vehicle is carrying human beings. Okay, so it should be, for most of the cases it should be foolproof. Okay, so how much values are there. Okay, so what are the instrument it can be used. Okay, and that is very important for that vehicles. Okay, then emergency disconnect. So suppose any normally it's not happen, suppose any adverse situation is occurred, so what you need to do, you have to disconnect your system emergency basis. Okay, so that is another important challenging issue. And finally, that converter, so which type of converter you are using for it. So just couple of slides back I have discussed what are the different types of converters and how they implementing vehicles. Okay, I hope all of you are getting my points. Okay, if any doubt is there, please let me know. Now, charging technology, what we can observe, if you more kilowatt charging means charging time is decreased. So more kilowatt means more fast charging is there. Okay, so uptime also be revenue. So revenue also be more basically. If you do charging for the peak demand, so definitely it will it having some effect in the revenue to revenue collection. Okay, so kilowatt, based on the kilowatt you can say like that, how much kilowatt, based on that, so how much revenue is required and how much revenue generation is there. Okay, then what you see that how do you install that charging station. So for the installation purpose you have to connect one three-phase transformer, or you say like that you have to install some separate system, and separate connection need to be taken and it's needed for your local electricity distribution centers, okay, or sectors. Okay, so some dedicated transformer is required with 33 kV. Okay, so dedicated transformer with 33 kV, so that's required for developing the charging station. Otherwise it's very difficult to run intercity, the run your vehicle in different intercity places. Okay, so more charging means more charging station means your investment is high. If your investment is high, so definitely costing of that unit price is obviously high. Okay, so here we can see different types of charger, like onboard charger. This is called DC output. Onboard charger, so box inside of the vehicle. Okay, this is onboard DC chargers. Okay, this is portable. Okay, that charging port is portable, but it is not onboard. This is onboard charger. Okay, so and rating you can see it is less, only 2.5 kilowatt. Okay, and from here you can see for onboard charger for DC output. Okay, it is rating 7.5 watt kilowatt. Sorry. Then here you can also see the AC fixed charging output. Okay, so fixed AC output is coming. It is more or less 22 kilowatt. It is also onboard charger. Okay, onboard charger, and finally here you can see the DC fixed DC output. So here you are directly connecting the AC to your system. Directly you are adding the battery. Okay, so that directly it is coming to that power. Okay, here you can see the bulk charger. So multiple charging units are there. And your multiple charging unit means lot of charging units are there. Okay, so bulk charging units, so accumulated value you are driving it for your system. Okay, so blank charging and DC output multi-channel. So for swapping station, you can say like that example. Okay, last one, bulk charger in the swapping center. Swapping center means where you are swapping your battery. Okay, suppose morning time when you are going to your office, so you keep that you keep your battery to the shopping center. Okay, so and when you are returning back, again you need to collect it from your sector. Okay, these are all the basic bulk charging stations options. So here you can see some diagram for different charging. Okay, different. Okay, 001 AC charging station, DC charging, DC 001. For the AC charging, the 001. So the rating is more, quite more. That value is 0. Sorry, 2000 ampere for the voltage of 48 volt, 60 volt, and 72 volt. Okay, so this is all that electric gun. Okay, so from where you are giving that connect your charging port to the battery. CS and Cardinal both are moderately same. Okay, both are moderately same. Okay, only the technology is different. Okay, this is from US based technology. It can carry more rating compared to your Cademo charges. Okay, so for the AC charging, what is the sorry, for the AC type 2 charging, what is the battery level, battery power level? It is 7.5 kilowatt for single phase. For three phase, this is 2.2 kilowatt. Okay, so you can implement them for your own charging infrastructure. So now what we are discussing about different types of chargers. Okay, so here you can see some diagram of the chargers. Directly you can understand. Okay, so these two are the charging stations. Okay, in your market area. Okay, uh, and what are the chargers? Normally two types of chargers are there. One is called onboard charger, another one is offboard charger. So onboard chargers means that inherently inside of your vehicles. Okay, And offboard charger means that it is not inherently connected to your vehicle. So onboard charger also having only AC charging is happen. For offboard charger only offboard charger AC charging as well as DC charging. Okay, both can be possible. Okay, so some diagram also given here for the better understanding. Okay. What are the different types of chargers? So it is onboard charger and offboard charger. Onboard charger, here you can see that electric vehicle, no charging unit is there inside of the vehicle. So it is connected only outside of the vehicle. And and next one is that offboard charger. So directly for offboard chargers, you can see that AC, DC, both the supply you can give it to them, and must communicate with the vehicles in order to supply the battery with the connect with the voltage and current. Okay, these all are the onboard chargers. Okay, different. Okay, so onboard chargers is the one and that most of the electric vehicle come to equipped with. Okay, by the onboard charger. For charging the vehicle, it takes AC from the outside using a fancy cable and the curves that challenges into DC and the transfer it to the batteries of the storage. So these are the very basics of here about the onboard charger. So now we can compare among all that mode 1, mode 2, mode 1, mode 2, mode 3 and mode 4. Okay. So consider we can do the considerations. Okay, what are the points are there for mode 1? So AC charging definitely AC charging methods from that household charging outcomes, so that we can discuss already. Then suggested, then supplying the circuit should have that RCD. So through RCD you have to supply it. So for that mode 1 AC charging is there is no communication protocol, so now no charging. Okay, so that is very basic. Next, for the mode 2 charging, there is a problem as this is slow. Okay, the response is slow. So, but it can be work it can be work of single phase, double phase, and triple phase also. Okay, charging cable is equipped. Okay, charging cable is equipped with an alternate cable control in the control box. So, automatically all are given for the precautionary purpose. Model 3, that what is your model 3? The AC supply from the dedicated EV socket. Okay, so whatever you are getting some supply. Okay, so from the EV. Okay, so directly you can connect the supply, single phase, three phase, two phase, whatever supply you have with the EV. Okay, so what you have to know first. Okay, what are the things like that? Okay. Then communication between the vehicles and the charger. So if the vehicles are coming, okay, and charging station is not free, so definitely that vehicle owner should be informed. Okay, so from the should be informed. So here it happens. Okay, so communications is there. Okay, so if you want to book that slot, so it will give some time. Okay, then after that you can only book. Okay. Then mode 4, the DC charging from the external charging. Mode 4 is high speed DC charging. So uh, the external charging means you are externally situated one charging station. From there you are fixed up in. From there you are directly connect your vehicles. Okay, from the charging station. Fixed charging cables in that charging stations. Okay, then enable flexible and controlled charging, that is 120, 70 watt, kilowatt respectively. Okay, so these all are the very important charging infrastructure sorry, for that vehicles. So here you can see some communication lines are there for mode 1 fixed, no dedicated socket. Okay, mode 2 is a non-dedicated socket with the cable incorporated protective devices. So directly bidirectional options are there. Okay, mostly the fixed and directed circuit socket. So directly it is connected. Okay, and 4, that is here you can see that AC grid also connected to the DC grid. So and that the DC grid you are connecting like a electric vehicles. Okay. Now sustainable transportation. So okay, directly we are discussing about the sustainable transportation. So initially, what we are talking the charging station, what you need to do, you have to take the permission from your distribution office, and you have to launch, not launch directly. You have to develop the charging infrastructure. Suppose solar panel will be from there is some cable, and that cable is going to charge your battery. Okay, so basic prerequisites are there. Okay, that I am considering solar. That's what I'm telling. So you can use other renewables also. Okay, those are feasible, working. Those having some feasible working idea. Okay, so here you can see the grid is there. After grid, what happened? Some after grid, you can see some switchboard. Okay, then directly you select that it is connecting to the microgrid circuit. Okay, and load side, what you will do, you will connect. You will connect two charging station, and two vehicles are going to charge from the charging stations. Okay. So bidirectional converters is there, that AC/DC conversion for that AC/DC conversion, bidirectional converter is required for charging and discharging of your battery. Okay, that is most important thing. And you can understand that when battery need to give or battery need to start, okay, or move, everything will be decided by that charging and discharging. Okay, so directly it can be decided by, you can see from the previous slide. So your mode of operations are there. It is discussed by your whatever structure you have used that. Okay. So then what is the benefit by using that your own past, what is the benefit for use your own idea, for installing the sustainable transportation? Okay, so you can also operate in that peak sharing conditions. Okay, suppose grid is not capable enough to sufficient energy, so from this one you can utilize, from this end you can also attend it. Okay, so different concepts are there, different charging stations are there. Okay, so how do you implement them? Okay, so peak sharing, grid balancing, emergency backup, renewables and integrations. Okay, renewables and integration means definitely power converters will be there that can that can processing your power in the peak conditions. Okay, grid balancing also be there, emergency backup, renewable integration. All are the most important features are there. So now I am talking about basic concept of charging points. So what are the different charging points? Number one is level. So based on the level one charging, level two charging, level three charging. For level one charging, you can see it is not more than 3.3 kilowatts. So restricted up to 3.3 kilowatt. Okay, the level 2 charging, what happened in level 2 charging? It the machine size is, what is the size? 7 kilowatt to 43 kilowatt, and voltage is 220 volt. Okay, ampere rating from the 30 ampere. Okay, so definitely that 30 ampere to 80 ampere for the single to three phase. So that you can go up to that value. Okay. Then next point is that level, next level is the challenges. Okay, what kinds of challenges you have taken? Sorry, different level 3 charging. So in previous case here you can see that level 1 and level 2 charging. Level 1 charging, this is 3.2 kilowatt. For level 2 charging, it is more or less, you can see that in normal AC charging, so 240 volt, and you can multiply with that 240 with 30 ampere, it is coming more or less 240 into 30, it is 7.2 kilowatt. Okay, so rating is twice of your level 1 charging. Okay, and level 2 charging, it is more or less high voltage, that is 400 volt charging, and timing also taking less time. So high voltage charging 50 kilowatts. So if you so how much current rating? So 50,000 divided by your 400 volt. Okay, so it is coming here 125 ampere. So huge current it is taking. Okay, and 80% battery pack will be charged by 20 to 30 minutes. Okay, so these are the different levels of charging. Okay, then different modes of operations. Okay, modes of operations means for charging mode, this is AC charging mode. Here you can see mode 1, mode 2, mode 3, mode 4. Okay, so basic concept. So mode 1 operations, they directly you are connecting your vehicle to charging stations. Okay, so there is no such communication protocol in between control and communications in between vehicle to vehicle to charging stations. Okay, but in case of mode 2, what happened, there is a residual current detections, means additional protocols are there. So additional protocols means, suppose that if you provide them, so that can if you provide them, so that can prevent, okay, that can prevent your system for overcharging conditions. Okay, so what kinds of preventions are there? It is slow charging from a standard electrical household socket. Okay, so slow charging for the standard electrical household socket, but there is a cable provides the moderate level of safety, so safety configuration is there. Okay, so what kinds of safety you can get? Residual current detections, residual current detector safety is there, over current protections are there, over temperature protections are there, protective earth detections. Okay, so different protections purpose, you can say like that, different protective protocols are there. Why it is important that you are talking about, everybody are talking about BMS, battery management system. So battery management system means it can taking different parameters of the battery, like battery current, battery voltage, state of charge, okay, the depth of charge, then battery state of health. Okay, so duration means how much duration it is turning on. Okay, so a lot of parameters it is taken and processing the unit, so that will be coming to the communication protocols. For mode 3 charging, what is, it is more or less similar to your mode 2 charging. Okay, and usually doing the EV which install the public locations and at your home and workplace. Okay, place is different. Previous one was there in your home, now it is there in the public place also. And mode 4 is the fast charging station, it is DC charging. Okay, so previous first three are the AC charging. Okay, and it is mode 3 is here, mode 4 is DC charging, fast charging stations. Always it having some communication protocol. Now here we can compare the different types of charging, AC and DC charging for America, especially America. You know that for AC, DC, both the cases you are using that for type 1 charging. Okay, so type 1 charging DC you are using CCS1 charging. Okay, and for AC you are using type 1 charging, that is J1772. Same thing for AC charging in Japan you are using that type 1 charging J1772. For the DC, the same thing is there in Japan. It is called Kademo charger. Okay, European Union that you are using that CCS2. Okay, sorry, for DC you are using CCS2. Okay, you can see different direction, different port. Okay, different structure of the port. Okay, so it is your guns having different structures. Okay, what are the points are there? CCS2 chargers. Okay, and Maneker chargers are using for European Union, that is type 2 charging, and for China both the cases GBT charger you are using. Okay, so only their orientation is different for AC and DC charging. And all market you are using the Tesla also introducing one charging. So everything is implemented. When one single charger you can implement it for your Tesla instrument. So different types of charging here you can see. Okay, so different based on the country and that application is given. For type 2 you are also getting. Okay, so socket for the type of case, so socket or plug is required. Okay, so what is the purpose of the socket or plug? So it can charging on charging station on cable towards the charging stations. Okay, so charging station to your vehicles. Okay, and inlet it is on vehicles to the on the cable towards the EV. Okay, so one is socket, one is inlet. Now here you can discussing about the backhand discussions of your charging station. That is your, you can say like that, ecosystem. Okay, so electric vehicle ecosystem challenges. What are the most important challenges or ecosystems for the charging stations? Okay, so that we are discussing about that FAME2, that high front end cost. Okay, so government is trying to reduce that front end cost. So what are the front end cost? Front end cost means you see like that, if you installing the charging station, so definitely there should be display. Okay, so that charging station should be install some area. Okay, so area means who will provide you the area. That place will be given by the government. Okay, so definitely that it should be the market area, or it should be the railway station area, or it should be the parking lot of different shopping mall. Okay, so that area, it should be the subsidized rate. Okay, that is one of the important upfront cost. Another one is the display. There will be some display, so it is written there is a charging station. So from uh, anybody can understand the display. Okay, so the charging station is there. Okay, next one is that CCTVs are definitely important. So CCTV camera, I mean surveillance is required. Otherwise, if anybody thinking that charging station is my personal property and keep it put it to keep it to their home, so it's not possible. So definitely surveillance is important. Okay, so basically the basic infrastructure related to your establishment or developing the infrastructures of your charging station, that is the upfront cost. Okay, so that upfront cost would be is normally reduced by that government, means you will get it subsidized manner. Okay, then utilizations. Okay, so utilizations means the utility. So how fast you are using the charging station. So is there any rush? Okay, so rush is there, or it is ideal conditions. Okay, ideally that means unutilized way it is waiting. So based on that utilization, definitely if rush is more, if waiting time is more, so definitely that is not so much cost efficient. So moderately you have to get it. So waiting time should not be more. Okay, always you will be having some car or two-wheeler or three-wheeler for the charging. Okay, so definitely utilization is one of the important challenges. Then operational cost. Operational cost means, so in the charging station, so it will take some time to charge the vehicle. So it will take some time. Okay, means the parking, there will be the parking. Okay, so parking space, the costing of the parking space. Okay, now the consumer. Okay, so now the service provider, consumers are providing, are sending the money to the service provider. Means those companies are installing the charging stations. They are sending the money. Suppose for 100 rupees you put on petrol. Okay, 100 rupee petrol like that. So they are also interested for 100 rupees you want to charge. So you have to send that 100 rupees from your mobile to that consumers, that service provider system. So the transactions. Okay, the transactions, definitely some additional deduction will be there. Okay, from service provider end. Okay, so it is called the gateway charges. Okay, it is called the gateway charges. Then parking charges, insurance premium. So all you need to give. So that's why operational cost also important, and provision of land. Okay, so space. So all the things are very important. Okay, and these are the basic challenges for the charging infrastructure, for development of the charging infrastructures. Okay. Now, if you suppose you are installing the one charging station, so definitely you have to design some app. Okay, so why that applications are important? Mobile applications. Suppose you are traveling. So one time what happened? Suppose you are traveling by a car. Okay, so you are having some Google Maps. So where you are going? Okay, suppose you need to know. So if your car having less charge, okay, you want to charge your car battery. So what you need to do? You have to find out your nearby charging station. So so like Google Map. Okay, suppose Google Map, what you need to do? So you make a search. You are having some app. Okay, suppose there are different companies are there who are providing the service. Okay, means charging service. So you have to install their own applications and you have to search it. Okay, so from your current location, then you can observe that how nearer the charging stations are there. Okay, how far is it situated. So okay, so how much time is required. Okay, if you able to see this place. Okay, now you need to know how much waiting time is there. Okay, waiting time is there. Then different charging facilities are important. Suppose what type of kilowatts are giving. Okay, suppose the charging station is there, but some works, maintenance works are going on, so it is not operational. Okay, so everything is important. Okay, so when you are developing that backend codes, okay, so charging station is the hardware infrastructure. Directly you put your charging gun to your vehicles, but you need to see see the status of that charging station. So how do you see? So definitely you have to believe some app. Okay, so that you need to know. So what are the important features like parking space? Okay, so when you are going to develop the app, so what you need to know that parking space is very important. Okay, so space for two-wheeler, three-wheeler, four-wheeler, and buses. Okay, how much space are there? So if you having bus, so that amount is provided by that one or not. Then yes to parking. Okay, space utilized by the commercial vehicles. Okay, so commercial vehicles, if you're going to there, so how much space are there? Okay, now load availability. Okay, charging infrastructure you have developed. Okay, so how much load you are going to operate? So it is 15 to 20 kilowatt or 50 to 60 kilowatt, 70 to 80 kilowatt, or how much kilowatts are there available? So okay, so civil works mean distance from your nearest source of power. Okay, so where you are there, so how far is it? Okay, so if you going to there taking shortcuts, so is there any blocking of your road, or all those things need to be updated? Okay, then visibility of the site. Suppose you are crowd areas. Okay, so charging station is the crowd area. You waiting with your vehicles, but you are not able to see the charging stations. Okay, how do you find out? So that visibility, site visibility also important. Then site footfalls. Okay, so suppose where you are having spare time. So for the charging, you have to wait, or you have to sit idle inside of the car. Okay, so better if you install the charging station in the place of tourist spot, or the malls, railway, bus stand, or metro stand, airport, restaurants, and other public activity centers. So directly they go there, they can come with their vehicles and going for the charging. Then they can do their own job. After completions of their activity, they can take the vehicles and return back to their site. Okay, so these options are there. So here you can see some Fortran charge, Fortran charge and drive. Okay, it's a Norway-based company. So okay, basic infrastructure for that company. When you are open their app, so what you can see over there in your screen. Okay, so directly you are having some vehicles. Okay, vehicle having some ISO standard. Okay, so there is a mobile app. Okay, so directly you want to see the charging end. So that and you are try to charge your vehicles. Okay, that is your charging stations. Okay, you are having some mobile SIM. Okay, so how much mobile number, so how much amount you want to put it. Okay, so that is important. So backend user interface. Okay, backend user interface means what are the important steps is taken care about by the organizer or by the companies. Okay, suppose charging stations, maintenance of the charging stations, what are the status of the charging station, then organizations, everything, system users, how much user at a moment can utilize it. Okay, customers, payment, and charging session. Okay, so you have to book the session from this duration to this duration. I want to charge my vehicle. Okay, like that. Okay, so if you're facing any, they are using EMSP app actually. So installations and if your charging station is not there, okay, sorry, shutdown condition. So installation, maintenance, repair, that should be done by that company. Charge connect to the cloud, like that. Every data will be connected to the cloud, so you can easily manage it or you can easily implement it. Okay, so installation of the charging station is quite important. Basically, you have to apply to your domestic. Sorry, that is called your domestic supply. Okay, so domestic supply end, and for installation on distribution transformation, distribution office you have to apply for. Okay, three-phase distribution transformer is required basically for the charging. You can see a lot of current is drawing by your vehicles. Okay, if huge current is drawing means the power the power is more or less constant, so voltage dipping is there. Directly if you connect your system, so your system may collapse. Okay, that's a separate connection you need to take for it. Okay, and power quality issue is one of the most important things. So what type of converter you need to use there? Normally power factor corrected converter you are using for the power quality, mitigating the power quality issues. Okay, so now battery energy storage solutions applications, what are the most important thing? That is peak saving. Okay, so peak saving means process reduce the amount of energy purchased from the utility company. So what you are telling, the when you are installing the charging stations, so you have to purchase the power from your company, some of the distribution company. So if you install some solar panel or if you are installing some microgrid, okay, your inherent microgrid, so that microgrid also store the energy. That microgrid also having energy storing system, means battery it's also having. So by that amount of power will be stored by your energy storage system. When your car is when any of the car is coming over there for the charging, so you can give that additional energy. Okay, so you can give your energy from what you have stored there directly. You can send back that energy to your vehicle storage. Okay, that is a good option. So you are making your system quite independent. Okay, when the demand is more, okay, the peak situations demand is more, that means peak situation, only you are taking that power from the utility grid. Okay, means you are getting the power from supplier. Okay. Thanks for a moment. Sorry for the interruption. So that you can that microgrid is there, so directly you can provide that your storage energy to your vehicles. Okay, vehicle storage. Okay, so when the demand is more, only that time you will connect your standalone system with the grid. Okay. Now load shifting means that BESS, okay, battery energy storage system, allow the business to shift the load from solar to grid and vice versa as per availability. So whatever schemes are there, you are preparing so that you can directly incorporate over there. So when demand is more, so you have to switch your system to that grid. When demand is less, you switch off your system from grid to standalone conditions. That system should be there. Emergency backup, so there is a critical conditions, how far you can go, and the standalone conditions, how much demand you can go up to standalone conditions. So some security reasons, some critical value of that energy SOC level of your microgrid storage. Okay, microgrid storage means standalone microgrid storage for your charging infrastructure. You are keep it fixed. Okay, after that whatever situation will be arise, okay, so keep it fixed for the any of the situation, and rest of the energy will be taken care by your will be coming from your utility grid. Okay. Then microgrids that I am telling. So connecting your system with the microgrids, renewable integration. So definitely microgrid is there, means the conventional source may be connected as well as the renewable also connected to your standalone microgrid. Okay. These all are the very basics of the battery storage solutions for the vehicles. Okay. Now that you can see that different labs on lab is there, manufacturing lab. Okay, so testing manufacturing lab for the e-mobilities. Okay, so that lab is in your Bangalore. Okay, so they are having testing facility. Okay, so where you are able to test your two-wheelers, three-wheelers, different panels are there, battery emulator up to 100 kilowatt, 160 kilowatt, 250 kilowatt. So that one is there. Okay, so where you are able to check your system. Okay, so is it violating any of the protocol, or all are thick, or then violating your protocol, or all are as per the uh, standard. Okay, so e-motor test bed for 150 kilowatt, 250 kilowatt. So all kinds of facilities are already there. So if you are e-vehicle manufacturer, you can directly go there and testing your vehicles. Okay. now so for the e-mobility science, what are the most important features are there? So here you can see the batteries are very much important. Okay, so what are the different types of batteries? Okay, that also important. Basically, you need to know about the facility, what kinds of facility you are getting from that battery, as well as the service. Okay, cell level of the energy, the chamber pack level, then different testing, temperature, preparation, everything you can see over there. Then services means capacity measurement, okay, characterizations, cycle life, okay, different things you need to know. So motor you are using, what type of motor you are using. So ranging of the motor, is it 30 kilowatt, 150 kilowatt, 220 kilowatt. Okay, so different characteristics of the motor is also very important. Then performance is important basically when you are going for the testing. Okay, so you have to prepare the data sheet. Okay, when you are procuring something from the website or online or any other externally, you are procuring something. So where the data sheet is very much important. So how it is behaving, how its characteristics are showing with the changing of the different parameters value. Okay, so in the testing lab, you are changing, the rating is high and your motor, whatever you are utilizing there, so you are testing your vehicle in different conditions. Okay, different conditions in form of performance, safety level. Okay, so different conditions you are checking and you are plotting all those data to the system, and finally you can develop the data sheet. Okay, and for the data sheet, it can be observed that it is capable to run or not. Okay, is the product is marketable condition or not? That you need to know. And for EMI, that definitely it's an issue. EMI or EMC issue basically, what type of winding or what type of connections you have done inside of your vehicle. So definitely it is important. So how much EMI value, EMC values are coming. Basically you are inside of that vehicles. Okay, so magnetic waves, how much detrimental for your case. Okay, that also important issue. You are also using that mobiles inside of the vehicles. Okay, so a lot of electrical connections are there. So how your mobiles are working on money? Is there any interference in between your communications or your system electricity cables? Okay, so that is very important issue for the testing purpose. Okay, now here we can see some comparison in between the BS6 and electric vehicles. Okay, so you can see that BS6 having definitely less pollutions, so no CO2, but EV has less pollution means less CO2. EV has no pollutions in terms of CO2, but there is a problem of drainage. Okay, that after completion of the life cycle of the battery, okay, so there is some issues. Okay, so drainage issue or recycle issue. Okay. So infrastructure is that models, different models are already available April 2020. Okay. So no BS4 vehicles registration production is happened after 2020. Okay. EV manufacturing has been said battery technology and charging infrastructure are at the rapid development in phase of India. So how much cost is it? It is approximately 70,000 for BS6. But in case of EV, it is coming cost around 90,000. Okay, for two-wheeler. Okay, similar features of your BS6 and that compared to similar features of your vehicle. So how much cost is there? Okay, so cost per kilometer in EV is coming per kilometer in EV compared to BS6 rupees 3 per kilometer with maintenance. But cost per kilometer in EV compared to BS6 0.6 rupees per with maintenance at is very low. So here you can see 20,000 differences are there. But most of the cases you can understand that the day it is quite cost efficient. That vehicles, okay, electric vehicles are quite cost efficient. Okay, what are the different vehicles you can see in our locality of India? So that you are using e-cart, okay, sorry, e-cart, it is called e-bike. Okay, that is less than 250 watt. Electric two-wheelers are there. Electric two-wheelers, L1, L2 category, different rating is high. Okay, e-rickshaw is there, or you can select an e-cart, four-wheeler passenger vehicles, M1, M2 was there. Heavy vehicles, it is also be there, M2, M3, e-auto. Okay, so their rating is quite high compared to e-rickshaw. Okay, so a lot of things are there. And you can see that golf course vehicles, that is very popular. You can also see it in the zoo. Okay, so hospital, airport, universities, resort, and railway stations. Okay, so you can see that battery drive vehicles. Okay, so in everywhere they're using that vehicles. So different four-wheelers are there. Okay, those are already launched in India, like Hyundai Kona Electric, Tata Tiago EV, Mahindra having different varieties of that EV. Okay, so they have already launched in India, and their cost is how much you can see also observe based on their rating. Okay, so here the another thing is that most important thing, that energy storage. We are discussing about that energy storage. So we are discussing about the energy storage means battery. Okay, so battery is charging, discharging, different things are there. So sometimes what happen, you are also very busy. Okay, so you don't have so much time to charging your battery. Okay, so what you need to do? So there is another concept that is called battery swapping technology. Okay, battery swapping technology means what happens? So directly you are purchasing different batteries. Okay, so when you are going to office, okay, when you are going to office, so you just there is a charging station. Okay, there is a charging station, and you are giving your battery to the charging station for charging purpose, and you take one battery from the charging station which have already charged, and connect your scooty or connect your bike and go to your workplace. And evening time when you are returning back, you just give that battery to them, and take your own battery and install it to your vehicle and come back to your home. That is called the battery swapping process. So you are swapping the battery. Okay, one in the EV battery technology, which is the fundamental battery swapping. Okay, so the standard EV battery with the characteristics of high mileage, high energy density, high recycling ratio, high recovery ratio, environmental friendly, ability to secure need to be developed. So that's the basic concept for battery swapping. Okay, so you are reducing your time. Okay, so here you can see different solar power station. Okay, solar power base your charging stations are there. Okay, so it having some obviously advantages also be there, disadvantages also be there. So charging stations also be there for the bulk charging. You can also use the battery swapping process. So what are the different types of battery swapping? Three types of battery swapping you can see. This is first one you can see. This is called side swapping. Means there is a battery charging station. Battery racks are there of your bus. Okay, so that is battery driven bus. So you are changing. Okay, you are changing that battery bank, power bank to your bus to the charging stations. Okay, and taking one battery bank to your inside of the bus. Okay, so every day it will be charged. Then after discharging again you can take it. Okay, then rear swapping. Rear means backside of your car, the battery pack is installed, directly you are changing it. Okay, then bottom swapping. So here you are just battery is there. Okay, so your car is your car is standing over there, you are changing that battery level from bottom of the car. Okay, so there are different swapping process is there, different types of swapping. For your e-cart, okay, that is your e-bike. Okay, directly this is your charging stations. Okay, so you are carrying your battery bank is there. This is your battery bank. Okay, directly the discharge, which battery is already discharged, you keep it, you give it to there for the charging purpose. Okay, and take one battery from this charging bank and install it to your bike and go back to your work. Okay, this is called that charging station, swapping station. Right now it's also just like a business model. This is also another startup. Okay, I hope that that Ola is right now in the big business for the charging infrastructure. Okay, so these all are the related to our EV. So here you can see in Bangalore the how on charging stations of the Bangalore. Okay, so how it will look like that. You can see a lot of panels are there inside of that panel when charging station. So different panels are there, and you can see the guns are connected over there. At a moment, 2 4-wheeler can be charged. Okay, so at a moment 2 4-wheeler. So here you can there's for installing your charging station. So additional power you need to connect from the distribution end. So distribution companies, you have to take the permission for the additional power line. Basically, it is 3 kV, sorry, 3-phase connections is required with having the distribution level. Okay, basically 100 kilowatt, 200 kilowatt, we are talking about that. So that's why additional connection is required. Okay, so here you can see some electric vehicles. Okay, inside of that, what are the different components? Okay, here you can see different components of a Hyundai Kona. Okay, so different components of the EV. Okay, there is a motor is there. Okay, so fuels, instead of fuels, here you can see the charging guns are there at a conditions. At a moment, 2 vehicle you can charge. Okay, 2 gun points are there. So intelligent analog battery pack. So we are changing the battery pack. So problem is that in swapping, so repeatedly you are changing sometimes. So due to the mishandling, the battery life may be change. Okay, so battery life may be problematic. Okay, it may be reduced. Okay, so that's why what you need to do. So better to charge your vehicles that is more efficient. Okay, compared to the swapping concept. So swapping concept only be there for very domestic, and if you have that sophistication to handle by that client, so then good. Otherwise, it is difficult. Okay, so there are different concepts like cooling system. So battery pack is there. So cooling system, battery management system, HV system, LV system. So a lot of things are additional things need to be taken care of by your battery pack. So fuel tank plus engine, both are using like a battery. That's why it is called the intelligent analogy of the battery pack. So fuel is behave, batteries behave like a fuel as well as that engine, means the driving force also coming from a battery side. So here you can see some EV battery. EV battery is engine plus fuel system minus rotation plus noise plus vibration. So that kind of things you can observe from here. Okay, so that's all from my side. So the session is more or less quite informative. So I hope some of the information you will get from this lecture. Okay, so if you have any other doubt, any other queries, you please ask me.
Any queries from the participants? But it seems everyone is clear with your presentation and they have understood it.
Okay, thank you. So if you're having any kinds of queries, okay, so please you can write me the mail. Okay, so I have given my communication details. Okay, so thank you. So
Thank you, sir.
thank you all.
Sir, just before a small vote of thanks for you. Thank you, sir, for giving a clear view of EV ecosystem in India and efforts taken by government to push for adoption of EVs. Sir, you have discussed about different types of EV chargers, charging options, concept of chargers, and battery energy storage systems, and many more aspects of EV system. This session was very, very informative, sir. Thank you, sir, for being with us for 2 long sessions, yesterday and today. And thank you very much, sir.
Thank you. Thank you.
Thank you, sir.